Good noon to everyone present over here. Welcome you all again for the next session of International Conference on Energy Conversion and Storage. I would like to invite Dr. V. Mohan Kumar to introduce the chairperson, Dr. K. Bhupati.
Yeah, good noon to one and all present here. So it's my pleasure to introduce our chairperson, Dr. K. Bhupati. He got his doctoral degree in Anna University. Later, he joined National Postdoctoral Fellow at Anna University. Then he moved to selected for in DST Inspired faculty. Currently, he is working as Assistant Professor of Chemistry, PhD, College of Technology, Coimbatore. So his area of research is synthesis of new inorganic crystals, metal organic chemistry, supramolecular chemistry, and density function theory. His special achievement is he deposited 7 new crystalline compounds in CCDC. So he got many awards and honors. The few I will mention here. Award as editorial board member by Science Journal of Chemistry, DST SERB National Postdoctoral Fellow, Best Postdoc Award, and Inspire Faculty Award. He received R. Gopalakrishnan National Award for Best Thesis in Crystal Growth Conference held at Tiruchirappalli. International Travel Grant attend 17th International Conference on Crystal Growth and Epitaxy held at Poland. So he received 2 funded from DST worth 35 lakhs and 18 lakhs. So he have members in many professional bodies, Society of Material Chemistry and Indian Association for Crystal Growth. In his research credit, he have nearly 25 research publications. So in the few words, I call Dr. Bhupati to chair this session.
Yeah, warm good afternoon to one and all present here. Thank you, Dr. Morgan, for the nice introduction. And now I'm going to introduce our innovative speaker, M.A. Reddy sir. Dr. M.A. Reddy sir is obtained his PhD in 2003 with the highest honors in the area of the material science and engineering from University of Bordeaux, France. He is currently working as a senior researcher level 3 at Institute of Research Hydro-Quebec, Center of Excellence, Transportation and Electrification and Energy Storage, Hydro-Quebec, Canada. From July 2003 to May 2019, he worked at the National University Singapore. Over the past 20 years, he has conducted leading research on material for energy storage, like cathodes, anodes, and supercapacitor and solid-state electrolytes, solar cells, electro and photocatalysis, including the novel methods of synthesis and evaluation of the properties of materials and development in situ techniques. Dr. Reddy has nearly published around 200 papers in various international journals, and also he has obtained H-index of 65 with over 15,300 citations. These have recently placed him within the top 20% highly cited researcher in energy, ranking 1,002 and out of around 1 lakh around 1,86,500 researcher in 2020. Then the Reddy is serving as a editorial board member in Material Research Bulletin and the Journal of Energy Storage, and as well as the several open access journals like Material Energies and Molecules, and regional editor of Nanoscience and Technology, Asia. And Dr. Reddy has conducted several workshops related to the functional materials and energy storage and conversion. And he had delivered 12 plenary talks and 14 keynote addresses and 62 invited talks and 18 contributed talks at the various conferences. His research won many awards in national and international conferences, and he won the outstanding.
And also, in fact, this is my first time I'm presenting my talk in your university, in your college. In fact, so today, since the talk, I'll try to first talk I'm giving, so that I'll try to make it a little more simpler, so that some students are able to follow what I research we are doing. So, so since sometimes people call it the thin film, so thin film means like working with some small amorphous or crystalline thin films, and some bulk means what they call as the prepared by in solid state method, or like really crystalline materials. So these are my, I told that, so since previously I was in Singapore, now presently we are in Quebec, we are the French and English speaking state. Especially January, February, you can see almost like everywhere covered with ice, especially here. That's why importance of the, sometimes people are working with hybrid electric vehicles. Again, the temperature, so will play an important, that's why we have to, accordingly we have to act. So that's why this will clearly show that climate condition vary depending on the geographical regions. So this is my outline of my talk. So again, I would like to thank you. Some of the work we did, this lot of the outreach school I did, work I did with based on the high school and junior college students in Singapore. In fact, people are able to present with the national, for example, these are the various sites you can see with based on the different type of category of the students. So again, like me, other students also, they're able to present in the various national conferences. For example, Intel International Example Science Singapore Science and Engineering Fair. These like mainly on the national conferences, and some other prestigious conferences like Intel International Science and Engineering Fair, and some people are able to present with the, other parts of the world, for example, Poland, Japan, etc. So, and also so we have done small public outreach within the local as well as some outside. So these are the small group. In fact, we to acknowledge. So at bottom we can see many people from India. In fact, some people they utilized our lab, and then they're able to use the facility. And then I think most of the people, I think they submitted actually most of the experimental work they did in our laboratory, and finally submitted this. I mean, almost nearly 3 to 4 PhD students have been trained in our lab. So these are my collaboration. In fact, you can see the starting from this with India, the different part of the university as well as different part of the world. So this is my research interest. In fact, today I'm going to focus on some exam mainly on lithium and some example on sodium, potassium, etc. In fact, I don't have much time to discuss about other part of the research. I'll try my best to explain some slides, maybe to be interesting for the audience. So we know that generally, presently, we have mainly three problems. For example, energy, environment, energy, water, and healthcare. You know, among them, these are the three important hot areas throughout the world. People are concentrating. Among them, today we are going to focus on the especially energy, specifically what they call as the renewable green energy. People are talking. In fact, we can get in different types, either solar, hydro, batteries and thermal storage, and the different type of sources. Again, I can tell that the energy storage and conversion technology interdisciplinary area of material science and engineering, both physics and chemistry. And sometimes I can call it the engineering also. Sometimes we hear if you work with a large scale, again you have to work with chemical engineers, mechanical engineers, and sometimes electronic engineers and automobile, etc. So in general, as a researcher or for example any doing bachelor, it is very important. Our job is to understand the basic principles of operation, and characterization tools are needed to understand the energy storage materials. So these are the global energy consumption. You can see compared to these are the very based on the countries. You can see that almost like we are almost top three. Uh, have widely used. Many people are using. For example, still this number may be increasing more. Like since nowadays future people, many people want using that what they call as a, so more energy. So that's why we have to look for the either by natural or parallelly people are looking for the what they call as alternative energies, especially renewable. So that idea behind this one is, for example, so one of the battery, assuming that the battery for the smart grid. So if you want to uh, store the solar energy or wind energy, or people want to use this battery for a use of the commercial vehicles, electric vehicles, or what they call as smart city or smart building, etc. So again, so you, for example, use of the electric vehicles, I think we can reduce the, for example, we can reduce the pollution as well as, so for example, environmental problems. Again, remember, depending on the storage capacity, uh, range may vary depending on the which type, either by smart grid or electric vehicles, or what they call electric vehicles, or plug-in electric vehicles, and portable power sources, and especially medical. So again, depending on the requirement, energy is going to vary. So these are the, so people, for example, people future think that not only in India, throughout the world, so especially use of gasoline vehicles, think that there is a lot of pollution in the major cities. That's why looking for the other alternatives, like for example, electric vehicles are the one of the alternative storage device. Another important use of the batteries, for example, we know that we have places like in India, we have huge solar sun. So if you want to store the solar energy, I think we need a low cost battery pack. So for that case, I think main issue is that we need a battery pack should low cost and more energy, so that automatically, so that we can store the more energy like that way. So another area is electric vehicles, what they call as autonomous vehicles. Here, this is like driverless vehicles. So again, we can reduce using this autonomous vehicles. We can reduce fuel consumption as well as people are calling to reduce the CO2 emission, and also finally we can reduce the traffic congestion, etc. And I think these are the future smart city development people have planned. Again, the main issue is that I think maybe we can reduce the traffic congestion as well as vehicular crashes, etc. So it will clearly shows that the main issue is that presently, I think anyway, each technology or including the electric vehicles, presently cost is also higher. So I think we have to reduce the cost. And again, so it's very important if you work with autonomous vehicles. I think we need a good infrastructure, especially if you're talking about GPS or sensor technology, all the things, especially places like remote places, everything should be. Uh, so that is very important for this use of these autonomous vehicles. So this one slide shows that the importance of these autonomous vehicles. I think people are working with a different background, either by mechanical engineers, electrical computers, and again the chemist and then physicist all to work together. In this, for example, you can see that is a computer is there, sensor. So in the sense that is a multidisciplinary, all the people have to work together. In fact, you can see these are the different type of companies are investing. So it means clearly shows that different opportunities. So now I'm going to define the classification of materials. As we know that materials are broadly classified based on the utilities. For example, civil engineers, they call it the construction materials or phase change materials, sometimes some cases especially temperature, and electronic materials, and example engineering materials, and pharmaceutical material based on physical properties, metals, semiconductor, insulators, and magnetic, again optical. And today we are focusing mainly on the energy materials, where especially energy storage, what they call for the electric vehicles or smart grid and other applications. So, so just I'm going to introduce, that everybody is carrying this type of mobile phones. So it contains, there is a small cell. If you see that bottom like pouch type cell, it contains the negative and positive terminal. And sometimes all people are carrying mobile phones that it contains some cylindrical cells inside. Our future, if you're running with electric vehicles, I think this type of this 1850 cells are put it in a different configuration with a big stack, and it looks like the big electric vehicle pack. back like that way. So remember, based on this technology or whatever it may be, our energy requirement, again the size and shapes is going to vary, although materials are same. So remember, if you work with the grid, mainly you need a transfer the quantity, especially if you work with the small coin cells or this pouch cell, the material requirement will be low. That's why, so for large scale, I think material cost should be lower and toxic, and so it is very important and low cost, etc. So again, I mentioned that there contains the positive means there is a cathode. So aluminum, any cathode material coated on the aluminum current collector, and anode we use a copper as a current collector. Separator is the things with the polymers to avoid the short circuit, and in between there is a electrolyte to movement of the ions from one side to another side. So cathode we call as, since a chemist, we call as sometimes positive electrode. So if you work with the lithium batteries, we call it lithium containing any metal oxides, or you can use different type of the oxide, different type of the compounds, etc. Suppose negative electrodes we call as a art is called as anode, and negative electrode both are same. And if you use lithium battery, lithium either graphite or tin and metal oxide, etc. Suppose same thing is replaced by sodium batteries. Again, you replace by sodium compounds and then sodium as a anode, or potassium means potassium compound, or sometimes people call as a calcium, magnesium, and then zinc, etc. Again, remember, if you use this type of divalent moraine, automatically mobility issues. And here, if you use liquid electrolyte, again we can go up to 1 or 1.2 volts, etc. Charge we call as oxidation, means and analytic scan and positive current. SOC means state of charge. Discharge also we call the reduction, cathodic scan, and negative current. So you have to remember, suppose you work with the cyclic voltammetry, these are the important points you have to remember. So electrolytes we call as, usually we use a monomolar LiPF6, CDMC, ionic liquid polymer, and solid electrolyte. And current collectors, we use a copper as a current collector and aluminum foil as a for the cathodes. Remember, usually copper may oxidize above 3.5. Aluminum we put here to react with lithium. Sometimes we may go to form with alloy with the lithium. So again, we need a binder to bind the materials, either cathode or anode. So then conducting carbon to improve the electronic conductivity, so that vertical people want to be fast charging and discharging, etc. So again, remember, so these are the important, I think all people are familiar about this 2019 Nobel Prize and the energy storage by well-known both physicist and chemist. So what I'm mentioning, that in addition to this one, another well-known chemist also, Michel Armand, also play an important role in the development of the intercalation concept or polymer batteries, etc. So I'm going to, as I mentioned, that the principle of batteries, it contains, there is a positive and negative. Again, the lithium, what is doing during the what you call principle, during the charge, lithium move from the one side, like positive side, to negative electrode, where the electron will pass to external circuit. So for example, this is a cyclic voltammeter graph, volt current versus potential, assuming this is a cobalt oxide. Here cobalt already is in 3 plus. Once you remove from here cobalt 3 to 4 plus, it means what we call as oxidation. And reduction means, we call as the reduction means, again go back to 4 plus to 3 plus. That's why we call it the redox couple. So again, the same potential, the galvanostatic plot, we plot voltage as a function of capacity. So as you can see that when you almost we get the same potential, and then almost like 3.9 volts, you can say. So in summary, if you talk about any cathodes, always you have to get a flat potential. For example, this another type of cathodes, we can remove this one, we can get 3.5, or vanadium, so we'll get 1.4.2, etc. So the voltage of the cell is nothing but difference between charge of the cathode minus anode. So that's why, as a layman or anything, so good batteries is to work with almost higher the difference between charge and discharge you to get. So that's why. So the now research is needed there by either by computation. That's why, or your density, anything, whatever the way. If any new materials in a different what they call as people can do different type of the what they call as computations, or try to understand how the electrode potentials are. Is there any way to look for a new composition. And that's why there is a lot of possibilities. I think people are working with the computations, and then are the DFT or so many things, ab initio calculation, etc. In fact, if you want, you can see the Professor Cedar is a well-known computational chemist, so he's working on a lot of interesting work is going on, that especially this type of the a lot of materials, it's a material genome project, etc. So again, the storage mechanisms, so broadly classified into intercalation. In fact, here 4 type of mechanisms are there. Among them, commercially energy storage mainly working on the intercalation deintercalation reactions, in the sense that we can get less volume variation here. If you talk about silicon, we can see that there is expansion. So also silicon, tin, these are alloy forming elements. So if you talk about the conversion type of oxides, in fact, I'm going to discuss about few example later stage. And alloy tin based oxide, if you cycle up to 1 volts and 3 volts, like again, so theoretical capacity vary depending on the you are charging, you are cycling the materials with which type of the voltage, etc. So what type of what people are called smart battery or smart battery device, it is very important. You have to get high energy density and high capacity, and adapt the climate conditions and long cycle life, and good coulombic efficiency, low impedance, and fast charge discharge. And again, you have to get, I'll tell you this later stage. Fast charge means if people are looking, there is any way to similar to filling the gasoline. So we can charge battery within 2 minutes or 10 minutes. Or, okay, so it's a little bit questionable, because main issue is that these are solid state materials. Diffusion of the like ions is a little bit difficult if you do with the fast charging. That's why. So at the end, if you solve all these one problems, you have to look for the more safer material, low cost, and toxicity. And at the end, you have to recall sustainable recycling. It's very important. If you want to too much of material, you have to get materials, and it's very important. So always you to look for the low atomic weight. So then only we can get higher theoretical capacity. So theoretical capacity is calculated by using the well-known formula. And anode should you have to get a lower discharge potential. Cathode you have to get a higher charge potential. I told you before, difference between the average potential, the charge cathode minus anode, give the working voltage of the cell, multiplied by capacity will give the energy density. So that's why always you to look depending on the which plateaus are looking like that way. So again, you have to look for the material should be very stable, in the sense that electrolyte won't react with either cathode or anode, and we have to look for the mixed ion conductance to improve the. So conductivity is also very important. For the insulator may not be really promising. So electrolytes are inorganic waste, either lithium, or if work with a different type of salt with different type of the chemistry, etc. So liquid electrolyte seems to be conductivity is good, and there is a problem with the flammability issue. That's why people have been replaced by liquid, liquid by polymer, or polymer with ionic liquid, or gel polymer electrolyte, etc. Again, with polymer electrolyte, I think we need a little bit higher temperature to get a reasonable conductivity. Separators already discussed. Separators are important factor, because we must use separator to avoid short circuit, and there is a thickness, porosity, and good chemical stability, etc. So again, so people use nowadays to avoid all these flammability issues. I think all solid state electrolyte means that we press the all oxide type materials are pressed together. Finally, we can sell. Again, these are very important factors. We have to look for high ionic conductivity, and electronic and low electronic conductivity, and good chemical stability with respect to temperature, in the sense that thermal coefficient, expansion coefficient has to match with cathode and electrolyte materials, and good chemical stability. It will no crystal structure or phase transformation should occur from the electrode material. Again, sintering temperature has to match with either cathode, and so this is very important. Sometimes the main issue is that while sintering that either cathode and electrolyte, sometimes there is a reactivity. That's why we have to avoid. So that is very important for the. In summary, use of these lithium batteries compared to our other type of system has been lighter in terms of higher volumetric and gravimetric. As a consequence, I think people can use for different type of applications, including portable as well as space application, etc. So these are the summary of the, if you're talking about the cost depending on the various component. So now I'm going to talk about the material processing and characterization techniques. So these are the various morphology depending on the which type of different type of the materials is possible depending on the which technique, which chemical method you are going to, or physical method. Depending on the technique, we can get the thing. So either you can try to prepare materials in chemical method or physical method, or sometimes people are actually mechanical engineers, I think, or sometimes ceramic solid oxide fuel cells. I think there we need a they don't we need a sintered good mechanical prop. For that case, we have to sinter the pellets. So for that case, I think we have to look for the what called spark plasma sintering or hot press, etc. So or sometimes recently what they call as additive manufacturing, or 3D printing, etc. So so again, characterizations, we are physicists or chemists, so at least it is very important. X-ray is very useful to understand the either cation mixing or impurities. Without X-ray, we cannot, since these are solids, I think we must use X-ray. Suppose if people are working thin films, I think we will need a Rutherford backscattering spectroscopy to know the composition thickness and nuclear content by nuclear action analysis, etc. And although this technique is a little bit expensive, that's why sometimes people cannot work with thin film. Sometimes we're not able to get all the paper will not publish. So at least we need to, people want to access this facility, we need the example, for example, Indore or Kalpakam, etc. So another the characteristic, for example, you can do neutron and then exorbs and X-ray absorption spectroscopy, etc. So sometimes the physical properties like magnetic, as well as, again, we need for energy storage, you need galvanostat and potential stat and impedance analyzer and morphology, etc. In fact, these are various characterization techniques, tools we are using, and these are various electroanalytical techniques. For example, since I don't have time to detail out the principle of individual technique. For example, if you have pellets, we need a high temperature studies or the impedance analyzer and battery tester and cyclic photogram, etc. So impedance spectroscopy is one of the useful tools. So suppose not only batteries, suppose people are working solar cells or so different type of energy, etc. So since I don't have much time to discuss all the things, and then sometimes people are happy. So again, so depending on the interpretation, depending on system, for example, supercapacitor or batteries or either cathodes or anode, depending on materials, your uh, uh, what they call as the resistance is going to vary, and then we can do some complex modeling based on the which voltage you're doing. And then again, so what summary is that I think there is a lot of literature is available, so at least you to read a proper original papers, I think you may get some idea. Suppose, for example, in a battery, before cycling, we can get a single semicircle after charge, so we can get a different type of, like, for example, bulk resistance, etc. So remember, so I'll always people they use a different type of the circuits like resistance capacitor combination, and they can do interpretation again. So depending on the which type of the system you're doing, that's why we need a knowledge on the both electrochemistry, physics, and material science and engineering, etc. So now I'm going to quickly go through a little bit other area. In fact, this is a typical plots. For example, if you do DSSC, so it's a good performing cell, you would get lower resistance. Automatically, we can get efficiency also. So these are very complementary. In fact, for the thin films, we can get by using either chemical vapor deposition techniques, physical vapor deposition techniques, or sometimes, well, nanopaste coating. People they use atomic layer deposition, etc. It is very important depending on application. We have to optimize thickness and composition, understanding the electronic and surface interface effects and mechanical properties are needed. So again, so there's typical sputtering unit. Suppose you want to get a thin films with hygroscopic materials, we can put the press a target, and we can, especially you can do sputtering, and you can open the cell inside the glove box. So interestingly, as a physicist, you can do a lot of physical parameters, the power, pressure, and vary the composition, deposition rate, etc. Again, depending on the physical and electrical and mechanical properties, depending on applications, we can do. So these are typical RBS report backscattering spectrum of the thin films. So when the helium beam is hits on the particular thin films, to the backscattered energy. So usual practice is that higher atomic number will come have higher channel number. So based on the RRM program, we know the composition and especially thickness, thin film and thickness. So we can calculate the composite thickness and the thin films. This is one of the best. So the typical micro battery or thin film batteries all are deposited by sputtering or by evaporation, layer by layer, either cathode, electrolyte, and then anode, and then the protective layer, etc. So these are the various cathode anodes. You know that cathode materials, the capacity is limited. Anodes, we have a lot of, there is a lot of different type. Again, I'll tell you that we have the different type of the problems with each type of materials. I'm going to discuss in the coming slides. So these are very promising cathode. Among them presently, I think more promising is like NCM. So with high nickel rich the materials are people are using, since they are getting high energy density, in the sense high capacity, nearly almost people are reaching around nearly 200 or 220 milliamp hour per gram capacity, etc. So this is one example. Suppose people want to prepare, we need a simple tube furnace either by oxide. So they call it the carbothermal reduction method or graphene thermal reduction method. So we try to obtain a metal oxide with the graphene and carbon, and finally exfoliate. You can heat the sample at the 650 to 850 degree, and we are able to get a respective oxides. So it's very important. So if you work with catalysis, there we need metals or a metal oxide with a more carbon. So that's why depending on applications, we have to get a different. So this is one example. If you talk about lithium iridium fluorophosphate, so we try to prepare the sample. Again, these are the here vanadium 3 plus to 4 plus hydroxy couple and reasonably good thermal stability. These are the samples prepared by carbothermal reduction method. I'm going to skip the details. So these are the electrodes fabrication, either 70, 15, 15, and finally I coated in the copper or aluminum foil and twin roll it and punching machine, and finally we can use this dry things and use the glove box. So for example, people are preparing large scale. Again, everything is automated. We can do either mixing, coating, all things is to do it by machine. So that's why they are. So again, the depending on the size, design of the cell, we can do. So typical coin cell, for example, you can put either cathode anode, the bottom cap, and put the sample coated electrode and separator and lithium metal. Finally, the cell is ready. We can do, for example, charge discharge cycling. So the typical example of vanadium fluoride is the charge and discharge potentials. As you can see, nearly 6 months we run the materials and reasonably good cycling stability. And also we check with impedance studies as well as the cycled electrode clearly show that this material seems to be. So another example is the vanadium based novel vanadium based materials. The advantage of this material is that we check in terms of iron phosphate. So reason 3.5 means 4.1 in the sense that the higher the redox potential is good for the applications. So again, so we try to use this ADA green synthesis approach. We try to prepare the materials, and then so these are the typical charge discharge potential, as means that almost like 4 volts potential we can get reasonably good when compared to the iron phosphate. Still, there is a scope to improve the further performance by optimizing synthesis or looking for the low molecular weight materials. So these are example of potassium ion battery. Again, we can see I told you that the mobility we vary depending on the here lithium seems to be good. If you go for potassium, the capacity will be slightly lower when compared to the lithium. Again, by optimizing the electrolyte, I think still people recently some few other reports. So already they are able to get slightly improvement in the performance. So another type of the lithium vanadium fluorophosphate, in fact, the early work we reported and then followed by different groups, including the Novel R8, etc. They've been reported based on this early report. So again, we are able to get 4 volts and reasonably plot potentials. And another new vertical H3PO3 materials. These are all the samples, the big crystals. Again, we have to optimize, and still there is a lot of scope to optimize this material. And sometimes another type of the lot of the polymer precautions. I don't have much time, so I have to skip these details. Again, if we talk about the sodium ion batteries, again, so remember, so for example, if you talk about the lithium, you may get 4.2 volts. If you replace by again the same sodium compound, so we get 3 point, in the sense that although we get slightly lower capacity and energy density also will be lower because of the intrinsic nature. That's why Anyway, for the stationary application, agreed. I think for that type of technology, cost is also is a main issue. That's why lower cost is needed for this type of applications. So I'm going to skip the details on the again the sodium. Again, the story is that same techniques with you can replace the electrochemistry, and you can do only we need nice materials, and we have to look for the what are the respective plathos, etc. So another anodes we call as, for example, people are talking about graphite seems to be good, and fuel air graphene and graphene. Although graphene sometimes high surface area, we can get high capacity. Practically, this type of plathos may not be really useful. That's why you have to look for the good applications. We have to get a potential should be lower is good. So these are the examples with the different type of. Still, this graphene-based metal oxide composites, I think people are using for the different type of the applications. So another few minutes, I'm going to discuss about the anode material, some few metal oxides, various either by intercalation type of oxides. In fact, there are a few examples. So among them, only Li4 Ta5O12 is one of the promising material because of the plot potentials, and reasonably, I told you that anodes in terms of it being nearly one polar potential. You have to look into the for the practical applications. So again, the TiO2 try again people can use either you try to prepare either by the molten salt approach. So the typical XRD patterns from the low temperature to high temperature, the surface area is going to be decreasing when we heat the sample in different temperatures. So again, so we have to look for the we have to see the how the lattice parameter and the here again here since the intercalation type compounds, I think we need a little bit more surface area and what they call appropriate crystalline particle size. So it clearly shows that if you go for nano size to some micron size, the energy storage performance is going to be decreasing, especially this type of the titanium based oxide, anodized phase, etc. So again, these materials, I think people are interested either by people can use. And we know that there are three different, apart from solar, silicon, solar cells, organic dye. In fact, this area is being covered by the different previous speaker. But I'm telling the DSSC use of this high surface area material, people can use it for the. So one few example, high surface area material seems to be slightly better efficiency when compared to the commercially used TiO2, etc. So yeah, anyway, I'm going to skip a little bit more detail again. Ferroscite, I think already people have been talked about the first presentation. So I think all the history and which type of prospects have been discussed. So for example, tin oxide, I think with use of the nano size materials, I think people can use it for other applications. People are looking for chemical sensors. So I think these are a lot of opportunities for physicists and chemists, and if it's some semiconducting metal oxides or yttrium stabilized proton conductors, people can use it for the chemical sensor, etc. So I'm going to, so in summary, use of the molten salt approach, you can try to prepare either lithium compounds or sometimes binary spinels, etc. You can try to prepare. I think you can play depending on the salt and temperature and morphology, etc. So alloy-based materials, again, so these are the small materials we can look into the literature. In fact, that belongs to our group. So again, so there is a lot of scope for you people. I think look for new materials, look for the lower potentials, and then understand the how the physics and chemistry of these materials, engineering properties of these materials. So again, a lot of small bunch of materials we will look into literature. So again, you see these various metal oxides have been looked at in literature. Again, main issue is that how to reduce the potential is a big issue for the practical applications. So I think I have another 5 minutes. I'm going to quickly go through a little bit. So again, nitrides, we try to prepare the samples either by thin films, either by cobalt nitride, bulk material, etc. Again, thin film seems to be better. So the reason is that we are able to get into thin should be nano size, and bulk sample we try to prepare the, although try to bulk material, again capacity will be lower. So main issue is that again the voltage hysteresis is a big issue. Although we claim that 3 lithium can be reacted by using nitrides when compared to the automatically we get higher capacity. Here also compared to oxide lower capacity. The main issue is that how to reduce the over potential is a big issue for the practical application. Again, some metal oxide people are want to work with either electrocatalysis or some metal oxide people can use it for lithium air or example aluminum air, etc. And due to time limitation, I'm going to skip the details and the supercapacitors. Again, safety is a big issue. That's why either I can do with oxygen release or do electrolyte or so the different ways, either by different type of things is possible. So what I call battery management is also very important. For example, how to monitor the big packs and by using the approach. Since we are electrical engineers, I think there is a lot of scope how to understand, for example, different type of the batteries, for example. So we have to monitor the big packs, how to voltage with respect to the different cells is during discharge. Again, the same thing. Since I don't, so what I'm mentioning that in situ techniques. So that's why you have to remember, don't any charge the battery. There is a limit. So make sure that. So don't exceed the limits. With specified limit only you can do. At least you can do zero point 0.2 or zero point 0.1 volt. Higher is fine. Don't go to higher limit. So anyway, usually for your charges, there is a electronic circuit to stop. So practically, if you want to research, so whatever the limit, so if you buy a pack, sometime make sure that you accordingly appropriate voltage potentials. You have to look into. At least we need some knowledge on the which type of cathodes are using which type of material. So this is one example. If you remove the lithium, expansion and contraction is occurring. That's why this is one of the in situ technique. Sometimes people can use neutron and solid state, etc. So I'm going next 1 minute. So I'll tell that importance of is very important. Future we are going to use the many batteries. I think we are almost like 11 metric tons of the batteries, spent batteries are going to be discarded. That's why you have to properly dispose it in the sense that you have to recover the material either by direct or hydrometallurgy and pyrometallurgy recycling. Again, I think there's a lot of technology been already demonstrated with a large scale application, different parts of the world, including that Germany, and then Japan, and then other part of the US, other part of the countries. So these are the different typical type of the recycling technology. You have to dismantle it, discharge it, dismantle and pre-treatment, and finally recover by using the hydro and pyrometallurgy. Pyrometallurgy seems to be more promising. So what I'm concluding, the efforts have been made with the various materials, and among them few examples are the, since I don't have a time to this, again, I think we have to look for the low cost material and long cycle life performing novel materials are needed. Again, I think we need the cooperation with scientists and engineer to fabricate the large scale applications. And thank you very much. So if you have any question, I'm happy to answer. If you have any other queries, okay, thank you very much. So I'm going to stop. Okay.
Thank you so much, sir, for your wonderful and valuable presentation. Audience, this session is open for the discussion. If you have any queries, and you can give in the text of chat box, or otherwise you can unmute your mic, then you can ask.
Or if you have any doubts, you can send me by email. Also, it's okay.
Yeah, if you want to have any queries, then you can. Sarg has given his mail ID, so just you make note of it. Then, if you have any kind of queries or any doubt or anything, then you can ask him directly. So, do you have any queries, audience?
So,
Sir, is it audible?
Yes, you can.
Sir, good afternoon. I'm Prakash from
Okay.
Hindustan. Sir, how lithium-ion batteries differ from supercap?
Okay.
Supercapacitor.
Okay. Yeah. Usually, remember lithium-ion battery. For example, lithium-ion battery. I told you that. So usually, supercapacitor is like surface charge storage, and then, for example, like supercapacitor only for the fast charging, discharging they can use. So, for example, energy density wise, supercapacitor will get lower energy density. For example, if you want to use mobile phones, we cannot use the supercapacitor. Remember, so I told you that principle, we have to get a plot potential. So for example, 4.5 volts or 3.9 volts, we cannot get by using supercapacitor. Supercapacitor only for the fast, what they call regenerative, fast charging, or sometimes for the different type of application. For example, if you use with your mobile phones or like for example EVs, I think there we need a metal oxides should be proper potential, so in the sense that suppose we cannot use anyway super cap, depending on the application, people can use as of the your mobile phones. I think we need a plot potential, for example the voltage, so that voltage only we get by using the lithium ion battery. So that's why I told you the principle. So during the charge we can get a plot potential, sorry I didn't prepare the another slides. I think I would have done comparison between the charge potential of the supercapacitor and example with a lithium battery, with a battery you could have good. So usually if you use aqueous based electrolyte, hardly we can go to 1 or 1.2 volts. So for example lithium based with a non-aqueous electrolyte, at least we can go up to nearly 4.8 or some, depending on the maximum potential, up to 5 volts we can go. So practically I think nowadays I think best potential we are getting is around only 4.2 volts. Okay, so yeah. Sorry, you can send me email and I can send you some more references that will be good for you. Okay.
Okay, sir. Thank you, sir. Thank you very much.
Yeah.
Any questions from the audience? Sir, ready, sir?
Yeah.
So one question is in chat box. I read it now.
Yeah. I think the difference between the lithium ion
battery
tech and the lithium
and ion capacitor technology. So what is the difference between lithium ion battery technology and the lithium ion capacitor technology?
Okay, usually lithium ion, when they practically what they call lithium ion means one is the metal oxide, like lithium cobalt oxide or NMC. Another side is the graphite. That is practically will tell nowadays. I think although sometimes still people are replacing with the graphite side by thin lithium metal side, because there is a problem with the lithium metal now. The technology is that is called lithium ion. So lithium ion capacitor means, for example. So, for example, LTO is one side, it means Li4 Ta5O12, and another side is the capacitor. The people they use either by carbon based one. So that's why again it is contains either a symmetric capacitor or asymmetric capacitor. The things is people can use it. Okay. Again, the problem with this another what a capacitor technology, the voltage will not get, So okay, so that is a little bit drawback. Otherwise, still depending on the applications, I think people can use this type of technology. Okay. So still more popular is the supercapacitor. You have to get a rectangular plot similar to the what they call graphite, what high surface area carbon. You have to get a so for that case, material should be more surface area. It's very important. For example, so batteries, you may ask you that people may test, for example, graphite commercial, hardly it is less than 5 meters square per gram. It's not like very high surface area. Or for example, NMC cathode. That is also, if I remember, is less than 10 meters square per gram. We don't need very high surface areas. Okay. For example, a supercapacitor, or for that case, really since the ions has to penetrate and then we want the fast charging, so at least we need a high surface area carbon, so that what the electrolyte has to penetrate. Okay.
Sir.
So and also people are asking about main disadvantage we can get while doing with miniaturized batteries. So again, miniaturized the main. Again, I'm telling that although, so as a researcher, although we do some, for example, so although academic research we climb some capacity. If you go for industry, although 100% we're getting the lab scale, if you go for industry, you may not get 100%. They say at least we can get 80%. That's why always you to aim for the high capacity in the lab scale. And if you go for industry, I think there the fabrication technology is different, and for example thickness of the electrodes will be very, that's why. So although here itself laboratory scale itself we get lower capacity, if I go to industry it may not be interesting. That's why always is very important, people are try to prepare the samples in the what they call as a small scale. Once they're happy, they can try to go for the scaling up the material. Okay, that's why miniaturized batteries. Okay, so again, frankly speaking, that although nowadays, as of now, I think people are not bothering about. Sometimes they're taking the existing material either by, again, I didn't discuss too many details and the system. Take one system and try to optimize by using, for example, you coat the surface, for example, cathode. So coating, you can improve further what they call as reduce the capacity fading, etc. Okay. Also, sometimes please kindly suggest depositing some depositing methods per. So usually, I don't know which way I am going to. Usually, depositing means the sense that if you use a sputtering, so the thin films you can do. My suggestion is that since you are a physicist, you can try the reality. Better suggestion go for the what they call a Dr. Blood technique is good, so that at least you can try to put a sample in what, for example, coating method you can do. I think that will be good for you people. Okay, so that
Sir,
that is advantage. Okay, yeah,
sir,
yeah.
actually, Dr. Shivadevi is asking the kindly suggest some methods of disposing the used lithium ion batteries. It's not
Yeah,
depositing.
she's asking about
Disposing.
dispersing and depositing.
No, sir, disposing.
Okay, okay. So the best way that like dispersing the slurry, if I remember dispersing the slurry, best way that, for example, you take a the small. I didn't. You take a small magnetic pellet and you take a binder and all together you by the mortar and pestle you put it and use of the NMP solvent you stir it for almost like overnight, so it will nicely disperse it. So but you can use a magnetic stirrer and magnetic pellet, we can stir it. I think that will be good for you to disperse the things. Okay, it is like simple, stirring it, you can do it. That is possible. Okay, make sure that don't try put too much of solvent. It should be viscous slurry. So if it is too much solvent, so for example, coating may not be good. So that's why by experience you will learn, and then make sure that try to avoid too less also don't put. So it should be material says to flow. For example, it is like ketchup. Like that way or slightly accordingly by experience you will learn. Okay, so that is my personal experience. Okay, if you have any a little bit more details, I think you send me email. I think I'm happy to answer. Okay, that's not a problem.
Thank you, sir. Thank you for our the wonderful talk and the session. And any other questions from the audience? Okay, so there is
Yeah,
no.
just a minute. Bhubali sir.
Yes.
Yeah, Mohan Kumar. Okay, yeah, please, please. Yeah.
Yeah, question from chat box. What is the main disadvantage one can be while going for
Yeah,
mini
sir
electricity?
has
Yeah,
discussed
yeah,
already.
yeah.
Sir has discussed
Uh,
already this one.
yeah, I think I discussed that one, all the point.
Yeah, yes.
Yes, sir, yes, sir.
Yes,
Yeah.
sir. Yes, sir. Thank you so much for a nice presentation on the lithium-ion batteries and energy storage materials. And Dr. Mohan, is there any information want to give now? Mohan Kumar?
Yeah, yes, no.
Now we can conclude the session.
Yes, 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 no.
Yeah, yes. So thank you so much, sir, Dr. Reddy, sir. And okay, hope we will touch in the upcoming days also. So thank you so much, sir.
Okay, okay. Thank you very much, and thanks for attending the talk.
Thank you,
And
sir.
then any clarification, happy to send by email. Okay, thank you very much. Okay,
Sure, sir. Sure, sir. Thank you.
and also say good health and stay safe. That's all. Thank you very much. Okay.
Thank you, sir. Thank you, sir.
Thank you, Reddy, sir. Thank you.
Thank you. Thank you.
Yeah, next we will.
Bhubali, sir.
Yeah, yes.
Okay, just a minute. Yeah, we call the Karthikeyan.
Karthikeyan sir came?
Yeah, Karthikeyan sir available.
Yeah, okay. Okay. Okay, next we will move on to the next innovative talk from Dr. J. Karthikeyan. Mohan, shall we start now?
Yes, no, yes, sir.
Yeah, okay. Dr. Karthikeyan,
Yes.
we welcome you for this international virtual conference.
Yeah, thank you, thank you.
Yeah. Okay. Let me introduce Dr. J. Karthikeyan. Uh, yeah. Good evening, one and all. First, I would like to introduce our invited speaker, Dr. J. Karthikeyan. Now, he's working as the DST Inspire faculty in the Department of Basic Science and Humanities, Rajiv Gandhi, uh, Rajiv Gandhi Institute of Petroleum and Technology, JAIS, Uttar Pradesh, India. And he has completed his doctorate degree in the Chikri Karakudi under the Department of Functional Material Division under the guidance of Dr. P. Murugan, Senior Scientist, CSR Sikri, India. And after his completion of his doctorate degree, then he's moved to Finland for his postdoctoral research and the Department of Applied Physics, Aalto University, Finland. Then he was working as a postdoctoral fellow since 2018 to 2020. After that, he got selected as a DST Inspire faculty. Since 2022 till the date, he is working as a DST Inspire faculty in the Department of Basic Science, Rajiv Gandhi Institute of Petroleum and Technology, JAIS. Okay. His major area of research is, and he is mainly motivated to study the physiochemical properties of the nanomaterials, which can be engineered on the basis of our practical requirement. And also, he is having the wide knowledge of the DFT calculations, and also using this DFT calculation, he can deduce the physical properties of the materials. Okay. And his main area of research is the growth of 1D and 2D nanostructure from clusters, and also he has the another interest in the electronic and magnetic structure of clusters, nanowires, and nanoseeds. And also he is having some another area of the research interest is the electrochemical properties of the nanomaterials for energy storage and energy conversion applications. Okay. So with his credit, he has 18 international research publications with the total citations of 241, with the H index is 7. And the scientific achievements and discoveries. So almost he has published 18 papers in peer-reviewed journals, and high throughput is having the wide knowledge in the DFT calculation to understand the post-modified the molybdenum chalcogenides, dichalcogenides, and he can able to explain the tunable edge magnetism in the molybdenum sulfide nanoparticles. And for the first time, he has reported the effect of the valence electron, the concentration of the structural stability, and the electronic properties of the molybdenum sulfide iodide nanoids. And he has found the best atomistic models of molybdenum sulfide iodide nanoids, which is in contrast of the models previously reported by the many groups. He has ultimately he found the electronic properties of the atomic models as well as the corroborated by experimental reports. And he has proposed the formation of the concealed defects in the molybdenum sulfide single layers and their catalytic properties for the hydrogen evolution reactions. And he has demonstrated the stabilization of the large size planar gold structures on molybdenum sulfide single layers without any doping or defects. Okay. And what are the grants and award he has received? To credit of his research, then he got selected as the DST Inspire faculty in the year of 2022 25, and he has got selected as the senior research fellow. Then also he has received the funds from the Department of Science and Technology, Science and Engineering Research Board, awarded the travel grant to participate the conference held at Singapore. And, and also he has received some of the academic award, DST Inspire and DST SRF, and he has received the best poster award at the International Conference on the Electronic Material 2016, organized in Singapore by the International Union of Material Research Society. And also he has received the best poster award at the International Conference on Advanced Material for the power engineering. 2015, the conference held it in India. And also he has awarded as the best poster in the Winter School of the Frontier in Material Science 2014 held at India. And also he has cleared the GATE exam, um, a gratitude aptitude test for the engineering at 2011. And also he has joined as a junior research fellow in the DESA Chikri in India. And he is also the gold medalist of the BSc Physics in the college level, the 2019. So with this credit, now I request Dr. JK to present his work. Now I invite Dr. J. Karthikeyan. Now you can present.
Yeah, thank you, Dr. Bhubadi, for nice introduction. Yeah, first of all, I thank PPG groups and the ECS 2K21 organizing committee for giving this opportunity to share my research work in this platform. Am I audible?
Yes, if you can, you are audible.
What are you able to see my slides?
Yes.
Right?
Yeah.
There is no problem.
Yeah, okay. Thank you.
Hello?
Yes.
Hello?
Yeah, Karthikeyan.
Are you able to see my slides?
Yeah, yes. Yes.
Okay.
You proceed.
Okay, thank you.
Yeah, okay.
Yeah. So today I'm going to present two of my work. Actually, the work what I'm presenting is actually doctoral thesis work of one of my colleague, Dr. T.K. Bijoy. I was also part of this work, and we did this work at CSAR Sikri, and the Central Electrochemical Research Institute, which is in Karaikudi, Tamil Nadu. Basically, in our group, we do density functional theory calculations for materials in general. And Mr. T.K. Bijoy, now he is doctor. Okay, Dr. T.K. Bijoy was doing his research on anode materials, and I was helping him as a senior in the lab, and we started working on anode materials of lithium-ion battery. So we usually start with experimental work, like we are inspired by some experimental work, and we started understanding those experimental work using density functional theory calculations. So Dr. M.E. Reddy has given almost enough introduction for lithium-ion battery. He has covered the entire width of the lithium-ion battery research, but it's difficult for me to again say the same thing, but yeah, I just give a short introduction for lithium-ion batteries. We use so many gadgets, electronic gadgets in our day-to-day life, right? So when you go and buy these gadgets, what you will prefer, first of all, the gadget should be portable, right? So you want to move with these gadgets. So, and it should be more elegant in design, and more, it should have more functionals and features. So if it is, if you want to have a device which is portable, or which is portable, that should have certain qualities, like it should be lightweight, and we always like thin devices, right? So if I give you two laptops, one is very thin and one is bulky, then obviously everyone will choose a thin laptops. And to make it thin, we need to focus on two things. Inside these electronic gadgets, we have mainly two elements. One is circuitry elements. So these circuitry elements are really made very small by using thin ICs. And now people are moving towards Armstrong scale, and people are working on semiconducting 2D materials to make transistors out of very thin materials. And so we can fabricate these electronic components at very small scale. And to work these electronic components, we also need power, right? We need to power them. So we need batteries inside these electronic gadgets. So these batteries should also be very small. So if you want to have a very small batteries, these batteries should have store more energy. That means it should store more energy per unit weight of the material, right? And we should be very careful while choosing elements for making batteries. So first of all, we should choose elements which are light elements like carbons and silicon, and these kind of light elements should be chosen. And it should also have a long cycle life. So we always want our devices to work for a long time, and it should be reusable. That means we will be able to recharge these batteries for so many times. And its main thing is safety. So we want them to be very safe. So the technology should be very well studied and tested, and it should also be eco-friendly. And very importantly, above all these categories, we want all these devices at very low cost. So we should also focus on cost of these materials, right? So what are the choices? Already Emmy Reddy has shown this picture. So if you, from this picture, you can clearly see that the lithium ion battery stores more energy per unit volume as well as per unit gram of the material, right? Then you can see a red color circle, which is actually a lithium battery. So lithium battery is still having more energy density. So can we use the lithium battery in our electronic gadgets? Yes, of course, we can use lithium batteries, but it is very dangerous. Why it is very dangerous? So when you do more and charging and discharging cycles, when you use this battery for a long time, the anode side is having lithium metal. So you know that lithium metal is highly reactive, right? So these lithium metals are highly reactive. When you do more charge discharge cycles for so many times, it actually forms a dendrite formation. Like it forms a very small needle kind of shapes. And these needles, what it is doing, it is puncturing this separator, and it touches the cathode part of the batteries. So when you connect a fully charged battery, anodes and cathodes using a metal, you are going to have a short circuit, right? When you have a short circuit, it can fire. So this is an undesired event. So we don't want to have such dangerous things inside our electronic gadgets, right? So always we prefer lithium ion batteries. What we do in lithium ion batteries, we don't store lithium in the form of lithium metal, but it is always stored in the form of lithium ions in both anode side and cathode side. So Reddy has shown already the anode sides and cathode side materials. So these without these electronic gadgets, we can't really imagine our electronic we can't imagine our life, right? So nowadays we everywhere use the electronic gadgets, and these batteries are very essential part of these electronic gadgets. So that's why Nobel Prize was awarded for lithium ion battery discovery. So these three professors, they got Nobel Prize. Professor Stanley and Professor John Goodenough, they got a Nobel Prize for the development of cathode materials, and Professor Akira Yoshino got Nobel Prize for the anode materials. Basically, he used a petroleum coke carbon as an anode material, and John Goodenough developed titanium disulfide as a cathode material, and Professor Stanley Whittingham developed lithium oxides. So they got Nobel Prize. And this is again a working principle of lithium ion battery. This is in a fully charged state. You can see that the lithium ions are stored in the anode compartments, and there is no lithium ions in the cathode compartment. Okay, so the lithium ions are stored when you connect them in an external circuit. So basically we use the electropositive character of lithium, right? So in the lithium ion battery, the chemistry of lithium is effectively used. As we know that the lithium is most electropositive element, it always gives the electron to the surrounding. It wants to be in the 1+ state. It wants to be as a lithium ion. So what it is doing when you connect these anodes and cathodes through an external circuit, it leaves the electron, then electron flows through the external circuit, and it does some work, and it comes to the cathode side and reduces the metal in the cathode side. and lithium ions are stored. This is completely in a discharge state, so we want to charge them. So we can apply a positive voltage and in the cathode side and negative voltage in the anode side. This positive voltage actually pushes the lithium ion towards the anode side, so lithium ions goes back to the anode side. So this is completely charged state. So what are the materials used in the anode side and cathode sides? Already Dr. M.E. Reddy has covered everything. Today I will be focusing more about the anode materials. In the case of anode materials, the well-known commercialized material is graphitic carbon. So graphitic carbon is a very well commercialized material. It has a theoretical capacity of 370 milliampere hour. This is a formula for calculation of theoretical capacity. Here in the numerator, we actually have the amount of charge stored in the material divided by the molecular mass of the molecular mass of the material. This 360 factor comes because we want to have them in ampere hour scale, ampere hour units. If you don't put this 3600, you will get your specific capacity in milliampere second per gram. So what does it mean? If you it means that if you have this material, 1 gram of this material in your battery, you can actually deliver a current of 0.3 ampere for an hour. So 1 hour you can deliver a current of 0.3 ampere if you have 1 gram of this material. So if you have a more and more theoretical capacity, you are going to have more and more charge stored in it. So one of such interesting material is silicon. Yes, silicon is having highest theoretical capacity. For this Zindel phase Si5 Li22, for this composition, the capacity is 4000 milliampere hour per gram. So if you have a 1 gram of this material, you can actually deliver a current of 4 amperes for an hour. So the problem with the silicon is its pulverization and poor interparticle connectivity. So it's a kind of alloying material. Reddy was already discussing about that. So when you add lithium to the silicon, it makes an alloy with the lithium. And during this alloy formation, there is a huge volume expansion. Roughly it's 400% volume expansion. That means 4 times it increases its volume. So it's actually not a desirable thing, because when you charge your battery, if the anode side is suddenly bulging, it is not going to be a safe thing, right? So your battery may blast. So it is not a desired thing. And but if you go to the carbon, it is very safe. And but the problem is it's having very low capacity. So similar to silicon, we can also have tin. That is also an alloy material. But the problem with the tin is it's again having pulverization effects as well as poor interparticle connectivity. And what about other forms of carbon? Yes, carbon has other forms, like it can exist in CNT, it can exist as a carbon nanotubes, and these carbon nanotubes are having a better capacity than graphites, but again, it is not up to the silicon or tin, right? Graphene is having 2 times capacity of bulk graphite, because when you take a single layer, theoretically you can actually store lithium on both sides. That's why the capacity of graphene is twice that of bulk graphite. So we can also use other oxide materials like tin oxide. These are all conversion type materials. So in this conversion type material, first the tin oxide reacts with lithium and forms lithium oxide, and then further lithium reacts with the tin and it again forms alloying kind of things. So as I told you, we do DFT calculations for understanding this material. So here I have shown an equation. These equation actually, Nernst equation actually relates free energy of the reaction and the cell voltage. So here DFT is very effective in calculating delta G. So if you can accurately calculate the delta G of these lithium reaction with these anode materials or cathode materials, you can calculate the potential of anode or cathode. And if you can calculate this delta G, then you know the number of electrons involved in the reaction, and this is Faraday constant, so you can obviously calculate the cell voltage. So basically, we are going to use density functional theory methods for calculating delta G for these anode materials. And these two, as I told you, these two problems are motivated from the experimental work. Okay, so these delta G's we are going to calculate using density functional methods. Basically, it's a quantum mechanical approach to calculate total energy of the system. As we know, these properties are mainly governed by electrons. Electron is a quantum mechanical quantum mechanical particle. So we need to use quantum mechanical approach for calculating the properties of electron in material. So basically, we need to solve the Schrödinger wave equation for the electron. So as we know that we can solve the equation for one electron, but if you go for more than one electron, it is not possible to solve a Schrödinger wave equation. So we need alternative approach. We can do a lot of approximation. So let us see what's happening in a material. In material, we have actually electrons and ions. There are many electrons and many ions present in the system. So first we need to construct the Hamiltonian. In the Hamiltonian, we have kinetic energy parts and potential energy part. And in the kinetic energy part, we have two terms. One is kinetic energy of nucleus and kinetic energy of electron. In the potential energy part, we have electron nucleus attractive potential and nucleus repulsive potential, and electron repulsive interaction, right? These three potentials are involved in any many body interactions. And what we are going to do, we are going to do some approximation. First of all, we are going to neglect this kinetic energy of the nucleus, because we know that the nucleus is heavy. So we are going to neglect this term. Kinetic energy of nucleus is not considered in our Hamiltonian. So we have only electron kinetic energy, electron nucleus potential, that will be taken as the external potential. The assumption is here the electrons are moving in the field, moving in the background of ions. So it is assumed that the ions are present in the system, the electrons are moving inside. So it's a reasonable approximation. Then we can actually take this term also from this Hamiltonian, because this is going to be a constant term. So when we do this calculation for every wave function optimization, we are going to assume that the ions are fixed. When the ions are fixed, the potential energy between the nucleus is going to be constant. So that can also be neglected from our term. So remaining, we have only three terms in this. So this electron-electron repulsion, it's not just a Coulombic repulsion. There are two more terms, because in a material, the electrons are simultaneously interacting with all other electrons, right? That simultaneous interaction is not really included in the Coulombic picture. So there will be a correlative motion between the electrons. So we need to correct this correlation. And then there is also spin associated with the electron. So there will be exchange interaction between the electrons. So these exchange interaction, correlation effect will also be included in the potential. There are approximations for including these potentials. So I'm not going into the details. So that's how we construct the we simplify our Hamiltonian. Then once our Hamiltonian is simplified, we can actually solve the wave function for every electron within mean field approximation, right? Or we can start with the mean field approximation, and if you solve the wave function for every electron, from the property of wave function, one can really understand that the wave function doesn't have any physical meaning, but the modulus of wave function, mod psi square of the wave function, gives a probability of finding an electron in any space in the material, right? So it actually gives the density probability of finding an electron from unit volume. So it's probability per unit volume. If you multiply it by charge of the electron, it is charge by volume. So your mod psi square is actually giving electron density. So we can get the electron density. Then the most important breakthrough in this field is the development of density functional theory. So the density functional theory was developed by Hohenberg and Walter Cohen and Kohenberg, and they got Nobel Prize in 1988 because of its applicability in many areas of science. What density functional theorem says, for any many body system, for example, for any material, the total energy is unique functional of electron density. So if you know the electron density of any material, if you can get the electron density for your material, you can actually calculate the total energy. So when you calculate the total energy, your entire chemistry, thermochemistry is done, right? So you can easily calculate all these free energy changes associated with your material. And the second theorem is very important. The total energy is minimized only for the right ground state density. So as I told you, we can't even solve the equations, Schrodinger wave equation for a 2-electron system. So when you deal with such an n number of system, we should actually start with some trial wave function or trial density, right? So when you actually start with the trial density, you will get some energy. From the first trial, we cannot say whether the density is whether your density is correct or not, but we can change the trial density. When you compare the first and second one, if the energy of second one is better, lower than the first one, actually your second density is very or second density is better than the first one, or we can say the second wave function of n electron system is better than the first n electron wave function. So in that way, we can keep changing the electron density and approach to the minimum of this energy. So when you keep changing this density, you will reach a point in which the energy difference between the previous and next iteration will be very small. There we can stop. That means you have actually obtained the right density for your material. So we can actually get the energy. So that's how we can get the total energy of the system using density functional theory. And we are just going to use this for your atomic systems. So as I told you, today I'm going to present two works, both are motivated from experiments. Already I talked about the problems associated with the tin or silicon, which are alloying type materials. Also the problems associated with the carbon type materials. The carbon type materials is having a low specific capacity, but they have very good electronic conductivity. There are many good aspects, but capacity is low. But here, one side, silicon and tin, they have a very good specific capacity. The problem is it doesn't have good electronic conductivity, pulverization, and then huge volume change. So these we don't want. So the first problem is colossal volume change, so large volume change in the alloying process. So to avoid this, what experimentalists tried is they actually fill this tin or silicon inside the nanotubes, carbon nanotubes. As we know that carbon nanotubes are mechanically very strong. So when these lithiation happens, actually all these alloying reaction happening inside the carbon nanotubes. So these carbon nanotubes act as a kind of shield, and it reduces the volume change in the material. And so in their experiment also, they have observed a very high capacity for tin filled multi-walled carbon nanotubes. So the mechanism, what is happening inside this material when you add this lithium in the anode compartment, especially during the charging cycle, you are actually adding lithium in the anode compartment. So what is happening exactly when you mix lithium with the tin nanoparticles? So we are going to use density functional theory for this. As I told you, it is really computationally heavy. If I'm taking a nanometer size tin nanoparticle and then put it inside a CNT, study all this lithiation, it is really going to be a challenging task. Computationally, it is impossible. Especially in India, we don't have that much computing power. We were having very small clusters, so we wanted to use atomic cluster as a model to mimic this reaction and see what is happening really in this nanocomposite. So we have chosen 4-atom tin cluster that is shown here. So this is 4-atom tin cluster. So this is going to mimic like a tin nanoparticle, we can say, and then we are going to add lithium to this. So these numbers in the parent in the bracket are giving number of lithium atoms added to the tin clusters. So when you add tin clusters, initially the rhombus shape was stable. When you add, when you increase the number of lithium atoms to this cluster, it turns into the tetrahedral shape. So it forms a tetrahedral shape. And when you increase more and more number of lithium, you can see that the lithium started forming lithium bonds. So also we can find that there is opening of these tetrahedral structure. Initially it is rhombus, slowly it is going to the tetrahedral like shapes, and again if you add more and more lithium, it is again opening up. It even breaks the tin bonds. So what's the reason? What is happening in this cluster system? When you add lithium atoms, actually the binding energy is in slightly binding energies keep decreasing with between the tin and lithium, and suddenly you can see that when n is equal to 4, it forms a peak. Though this form of the cluster is called Zindel phase cluster. That was the main reason we chose this SN4, because these Zindel phase formation can be really mimicked by the small cluster, which is happening in the bulk form also. In bulk form also, tin lithium alloys form Zindel phase, and these Zindel phase formation can be mimicked by using a very small cluster system. And then when these Zindel forms are formed, actually all the bonding states are filled and anti-bonding states are left free. So you are getting maximum homolomer gap for the system. That gives a highest stability for the Zindel phase. Then when you add further lithium atoms, as I told you, the lithium always gives an electron to the material with which you are adding this lithium. So it actually donates more and more electron in the antibonding orbitals of this tin atom. So when antibonding orbitals are filled, we know that the filling of antibonding orbital is going to reduce the bond strength of tin atom. So because of that, the tin loses its tin-tin bond. Some extent, it completely breaks the tin-tin bond. After, we can say after 7 or 8, we can say that the tin-tin bond is completely broken. So we are going to use this lithiated tin clusters, and we are going to put it inside the CNT. So we want to understand the composite of tin lithium alloys inside CNT. So when you grow this material, actually the cluster size will be controlled by the CNT that you have chosen for experiment. But since we are doing it in theoretically, we have to first get the proper CNT size for inserting these clusters. So this is the adsorption energy. So we have calculated the adsorption energy for various tin clusters with various number. Means I have varied the lithium numbers, and I have filled these clusters inside various size of CNT. I have chosen armchair type CNT because it is metallic. We have also tested the same thing with the chiral and zigzag type CNTs, and we can see that for SN4 Li4 and SN4 Li6, 8x8 CNT is more stable, but only for SN4 Li8 this 9x9 CNT is stable. So in future calculation, if I'm mentioning SN4 Li4 cluster, that means it is inserted inside 9x9 CNT. For other clusters, I have taken 8x8 CNT. So what will happen if you put a very small cluster inside CNT? It is going to stick with the one side of the wall. Obviously, since all the atoms are not interacting with the CNT, it gives a very less adsorption energy. For optimum size, it gives more adsorption energy. So we have taken optimum size for insertion of lithiated tin clusters inside CNT. Let us check the mechanical property. What is happening? So here I have actually measured the diameter along X direction, A, the diameter along Y direction for single wall CNT as well as multi-wall CNT. So as a case study, I have taken SN4Li8 system. So you can, for a single wall carbon nanotube, the difference between A and B, that means that this deformation of CNT is very large. So we can say the difference is 0.86 Armstrong. the A by B ratio is 1.07. But if you go to multi-wall CNTs, the A by B ratio, actually we have measured it for the inner inner CNT. So the for the inner wall of this multi-wall carbon nanotubes, the difference between A and B is only 0.26 Angstrom. And so this clearly shows that when you use a multi-wall carbon nanotubes, the mechanical stability is really achieved. We can really control the expansion of these tin lithium alloys during charging process by using this multi-wall CNT and tin nanocomposite. So what is really happening, how it is interacting with the CNT? So we are always interested as a theoretician, we always interested in interaction, what type of interaction is present between these tin lithium alloys between and the CNTs. So we studied the charge transfer between the tin lithiated tin clusters and CNTs, and in all these cases you can find that the lithium is actually interacting with the pi ring of the pi ring of these carbon atoms in the CNTs. So there is a cation pi type of interaction in all these composites. That gives a better stability for this tin lithium clusters composite with the CNTs. And we have actually measured these tin bond and tin lithium bond and lithium bond. And very importantly, I want to show this lithium bond in a inserted cluster. We can see that the blue one, the blue charge clouds indicates the depletion of charges. The red one is excess charges. So that means that lithium bond distance is really decreased when you insert these clusters inside the CNT. That means the when you have these clusters inside the CNT, it actually donates some electron to the CNTs pi star orbitals. That we are going to see from the electronic structure calculation. We have calculated the density of states for various tin lithium clusters inserted CNTs. And you can see that without any lithium, there is not much changes in the density of states. The shaded one is the density of states of pristine CNT, and the black lines are showing the total density of states of tin-filled CNT. So there is not much changes. A very small shift towards the Fermi, but it indicates that its interaction is not favorable. That's what we have obtained here also. The interaction, the absorption energy is negative. That means it is endothermic. Whereas for other lithiated clusters, it's exothermic. That means the composite formation is feasible, energetically feasible. So now we can check the density of states for lithiated clusters. So when you add a lithiated clusters in the CNT, you can see that the density of states is shifted away from the Fermi, especially the occupied levels are shifting away from the Fermi. That means it actually gives an electron to the CNT's band. So that we can actually clearly see from the band structure calculation. So this is the band structure calculation of pristine tin CNT composite. So here I have shown the energy levels of tin clusters by okay, the energy levels of tin clusters are very straight. So they are molecular levels. There is no dispersion of bands. Also, we can see that the dots are indicating the electrons filled in the tin p orbitals. So when you add Li to SN4, so when you add Li to SN4, you can see that the this is the band position that you can take it as a reference. When you add a lithiated cluster, it comes down. That means this band is now occupied. So now if you add more and more lithium, now the band, that same position is going down. That means more and more CNT bands are occupied. But after a certain limit, that cluster is not donating not much charges to the CNT. And what is happening now, after a certain limited, the lithium goes to the interstitial voids of this CNT assemblies. So now the intercalation is happening between the CNTs. So we have actually calculated the intercalation energies, and this picture gives a whole energetics, what is happening in this composites. So here I have calculated two things. One is alloying energy. So this gives how much alloying is happening, which is dominating process that we can understood from this graph. And this is absorption energy that we calculated for this thin lithium clusters inserted in the CNT. And when you have a less number of lithium, actually these alloying energy is dominating. But after this N is equal to 4, after formation of Zindel phase, it started forming the composites. So the absorption energy between the tin cluster and lithiated tin cluster and CNT is dominating. That means first the alloying between the tin and lithium is happening. Afterwards, it starts making composite with the CNTs. That the interaction between the CNT and lithium is more favorable. That will be more dominating process. Then we calculated the intercalation voltage for every step. So the dotted lines are actually intercalation voltage calculated for every step. So here again you can see that the intercalation is not a dominating process. That intercalation becomes a dominating process when you reach N is equal to more than 6. That means first the alloying happening, then the composites are getting more and more stable. Once composites are completely formed, and then the lithium goes to the pores of CNT walls. It goes to the pores of CNT walls. So that's whole energetics. So these work really gives a understanding on these nanocomposite using a toy model. We can say it's a toy model because in real material we have a tin nanoparticles, but these nanoparticles can also be mimicked by using the small atomic clusters. So we have studied the structural, electronic and electrochemical properties of these nanocomposites, and the main stability of these composites are coming from the cation pi interaction between the lithium atoms in tin lithium alloys and CNTs, and the volume expansion is really minimized when you use the multi-wall CNTs. That is also demonstrated in this work. So this is the second work. In this second work, we have actually silicon carbide nanoparticles. It's actually surprising result for the experimental group also, because I have given the resultant discussion session. So here you can actually find that their original goal was to find get the silicon nanoparticles filled inside the carbon nanotubes. Filled inside a carbon coated structure, right? So that is their ultimate aim. So they want to prepare a silicon nanoparticle covered with amorphous carbon. So that is their ultimate aim. But what they obtained is an entirely different thing. They obtained silicon carbide nanoparticles instead of getting a silicon. And they, without getting these understanding, they started doing charge discharge cycle. Then the charge discharge cycle was giving very, very low capacity on comparing silicon, but the cycle, the capacity was retained even after 200 cycle, right? So the capacity is retained. It is not really expected from a silicon nanoparticle, but for a silicon nanoparticle, we are expecting more capacity, but the capacity should fade when you go for more and more cycles. But later they understood that they have really formed a silicon carbide nanoparticles, and they published this result, and they were actually not understanding what is happening really in the silicon carbide nanoparticle, because silicon carbides are insulators, right? So usually we don't use an insulator in electrode material, but here surprisingly they have got a very good capacity for a silicon carbide, and they started asking us to understand what is happening really in the silicon carbide nanoparticle. So we started again making a toy model kind of thing. So we have taken silicon carbide bulk structure, and we cleaved nano surface slabs, and we actually first studied the surface slabs for different thickness. So we can, here I have shown a surface slab of thickness 4. So if you, I have studied up to 10 atomic layer thickness. So when you study this, when you reduce the thickness of the surface slab, suddenly after 3, it started forming graphitic layers. That was interesting, because when you start with the zinc blende kind of structure, and suddenly when you reduce the size, it forms a kind of a graphitic structure. So these graphitic silicon carbides, then we started searching papers in this direction. Then we found already people have reported this. And these silicon carbides and zinc oxide and many such zinc blende structures, they form this kind of graphitic kind of structures. Then our idea was to exploit this or study this formation of graphitic structure when you add lithium. So that actually, that was a very interesting observation. So we started studying lithiation in this silicon carbide nanoslabs. Before studying the lithium interaction with these nanoslabs, let us study the band structure. So we have calculated the band structure for a single layer of silicon carbide. So that has a very high band gap. And then we have also tried 3 layers. Here for 3 layers, you can see there are 3 bands coming from 3 layers and 3 conduction bands here, and the band gap is slightly reduced. And this is coming from the top layer, and this is coming from the middle layer, and this is from the other side of the layer. So these are coming from 3 layers of this graphitic silicon carbide. And this is actually a zinc blende structure of a real surface slab. So in this surface slab, the band gap is really small. The band gap is very small because of the surface states. So we have actually calculated the density of states, and the corresponding density of states orbitals are plotted here. So you can see that these states marked as 1, 2, 3, 4 are actually really coming from the surface of these silicon carbide nanoslabs. So these band gap seems to be very small because of the surface states, but these can be really avoided if you add a kind of hydrogen or any kind of capping atoms on the surface. So if you add a capping atoms on the surface, you are going to eliminate these surface states, and you are going to open up a very large band gap for your silicon carbide. So then we studied the lithium adsorption on this silicon carbide. So as usual, we want to understand the energetics of lithium on this silicon carbide. So we put the lithium on different sides. So one is we can put the lithium on the surfaces. So this surface is carbon terminated surface. This is 3 coordinated carbon on the surface. Here this surface is actually a silicon terminated surface. Here we have silicon in 3 coordination. So we can put the lithium on the surfaces of carbon terminated side, or surfaces of silicon terminated side, or we can also right below the first layer of silicon carbide, or below the second layer, or below the third layer. So we can put the lithium in different sides of this surface slab, and we got the energetics. So these energetics actually is telling that the interaction of interaction of lithium on the surface is really exothermic. It's releasing so much of energy. That's what in the experiment also they have found. When they add the lithium first, it gives a very high potential. Then when they add more and more lithium, the potential comes down and it becomes a very slight potential when the lithiation is happening in the bulk. So let us see. We are going to take this order. So based on these energies, we are going to add more and more lithium to this silicon carbide, and we can calculate the capacity also. And let us understand what is happening in the lithiated structure. So as I told you, this is for the pristine surface slab. There are surface states. But when you add a lithium, you can see that the one band is disappearing, the black one is disappearing, because we have actually added a lithium which donates 1 electron to the surface atom. That quenches the magnetic moment, that quenches the surface, that kills the surface, that kills surface states. But when you add a lithium just below the first layer, actually now you can see that there is a band which is shown in a purple color that gives a band of a single layer. You can see that when you add a lithium in the right below the first layer, it forms a graphitic layer here. When you add a second layer, it forms 2 layers of graphitic layer. When you add this below 3 layer, it forms the 3 layers of graphitics. When you add when it goes near to the other side of the surface, it forms a graphitic layer on the other side. So these lithiation actually induces, or it increases the tendency of forming graphitic silicon carbide layers. That is our understanding from this lithiation, and we made it as a mechanism for these silicon carbide based anode materials. So the mechanism of these anode material was really not understood previously, but so many people started using silicon carbide as a nanomaterial. So we added more and more lithium, and we wanted to see how much lithium this can store. Actually, in the earlier work, in tin based work, we didn't go for the capacity calculation, because if you take a we took a very long CNT model. So if you add lithium on every hexagonal ring, that's going to take a that's going to be very computationally heavy job. So we didn't do that. But here it was like a very easy job. If you add a lithium on top and bottom of the silicon carbide layer, it forms a very interesting structure of Li2SiC. So the middle layer is graphitic silicon carbide. On top of the silicon carbide layer, we have one lithium, and the bottom of this having the second lithium. So this is actually Li2SiC layer formation in this. So we have actually increased the number of lithium atoms. When you add a lithium on the surface, obviously it produces a lot of energy because of the lithium interaction with the surface undercoordinated atoms. But when you increase the number of atoms, it goes to the bulk of silicon carbide nanoslabs, and these average intercalation voltage is really low. That shows it's a really good anode material. And also we have calculated the specific capacity for Li2SiC. For this composition, it is coming to be 1300 milliampere hour per gram. So that is what experimentalists they have observed. They have obtained this capacity for nano silicon carbide. They tested it for a commercially available silicon carbide particles also, because that was larger in size. But when they reduced the size, they could achieve a really high capacity. So the high capacity comes because all these silicon carbide layers are forming graphitic structures, and that gives a very high capacity, and that capacity is also matching with our models. So that's a finding from DFT. So it really gives me a pleasure that DFT is a very powerful tool to understand atomic levels, what is happening inside electrode materials. So we have actually studied the electronic properties of silicon carbide nanoslabs, and then we understood that even without lithium, it forms a graphitic SiC layer. That was starting of our work, and we started using lithium for making this graphitic SiC layer, and we understood their electronic properties and their electrochemical properties. So basically, we have calculated the AAV, that's also matching with the experiment, and the specific capacity is also matching with the experiments. And take-home message is this: the DFT is very powerful technique to understand the properties of material at nanoscale, or we can say atomic scale. So more information atomic level scale can be get from the DFT. When your experiment is not able to solve some problems, really DFT is going to help you. And then electrochemical performance of these electrode materials can be accessed with the decent accuracy, and that's what Dr. Ashwin also demonstrated in the morning. And again, these two works shows really how the DFT can give a decent accuracy for these materials properties. And we can, when you get more atomic level understanding, we know that we are going to move our development of technology in the right direction. And I thank my supervisor and my colleague, Dr. T.K. Bijay, who is a postdoctoral fellow now in Indo-Korea Science and Technology Center, Bangalore, and my mentor, Professor Vijay Kumar, who has given a lot of support, and he has guided me in all my careers. So, and then funding agencies, of course, without funding agencies, we can't do all this scientific work. And then finally, last but not least, but I like to thank my present institution, Rajiv Gandhi Institute of Petroleum Technology. It gives a really vibrant research environment here, and for setting up my own computational research lab at Uttar Pradesh. Thank you. Questions?
Thank you, Dr. Karthikeyan, for your wonderful and inspiring presentation. And I request to audience, if you have any queries, and you can give it in a chat box. Now the session is open for the discussion. Audience, if you have any questions, then you can ask me now. And one question is there, Karthikeyan.
Basically, we need to, for the calculation of specific capacity, basically we need to understand the composition. So if you know the composition, then we can calculate the theoretical capacity. I'm talking about the theoretical specific capacity. I showed theoretical specific capacity of these materials. So it depends on the molar mass and the composition, and we know how much electrons are involved in the system, so we can calculate. But experimentally, one can get how much lithium is really inserted. That you can calculate from that, or from the capacity you can calculate. You can in a reverse way you can calculate the number of lithiums inserted in the electrode materials. So that's going to be reverse calculation. You measure your capacity, from that you get the number of lithiums inserted in the anodes or cathodes.
Any other questions? Audience, any other questions from you? Okay, I think there is no more questions from the audience. Dr. Morgan, can we conclude this session now?
Yeah, yes, ma'am. We conclude now. I
Yeah,
hope
okay.
the participants enjoy the presentations. If you have any queries, please mail to Dr. JK or mail to us.
Yeah, I have also given
revert
my
you.
email ID, so you can contact me in this email ID.
Thank you, Dr. JK.
Yeah, thank you, Mohan Kumar, for this opportunity.
Thank you, sir. Thank you. I thank Dr. Bhubadi for chair the two sessions. Thank you, Bhubadi, sir.
Thank you. Thank you, Dr. Morgan.
The participants, just hold on. The participants, the oral presentation ID already mentioned to you and scheduled sent to you already. So participants, be ready. OP57 Maheshwari.
Yes, sir. I'm audible,
Yeah,
sir.
just a minute, ma'am. Just a minute.
Yes.
Yeah, OP57 and OP90 ready. So any other participants, oral presentations?
Yes, sir. My presentation, sir.
Just a few minutes. Announcement for poster presenters.
Dear participants and presenters, an instruction for you all. For poster presentation, all the participants are requested to visit our conference webpage icecs.live, and if you have any queries, you can use of comment section to clarify your doubts. For first time, we will approve your ID in comment section. Then from the next questions onwards, your ID will be active. For oral presenters, if you receive any comments regarding your poster, the same procedure will follow. Thank you. Next, I would like to invite Dr. V. Mohan Kumar to introduce the chairperson, Dr. Ira Pave.
Yeah, good evening all. It's my pleasure to introduce Dr. Pavai. She has completed her doctoral degree in Pachapas College, University of Madras, under the guidance of Dr. Murugathan. To her credit, Pavai Era has published over 20 articles in peer-reviewed international journals. Currently, Pavai working as an assistant professor of physics in B.S. Abdul Rahman Crescent Institute of Science and Technology. With immense pleasure, I would like to invite Dr. Pavai to chair this session. Pavai,
Yes, sir.
the session is yours. We call the presenters one by one. You can share this session. So also,
Sir, thank you,
I
sir.
ask other invited speakers. You can also comment any comments in our oral presentations. Thank you.
Yes, thank you, Dr. V. Mohan Kumar. Good evening to all participants and the organizing committee and other invited speakers. Now, shall I call upon the oral speaker OP number 57 to present your paper? And before that, I would like to make sure that you all need to complete your session within 5 minutes, and your prescribed time is only 5 minutes, and try to wind up as early as possible. Yes, you may start. OP number 57.
Good evening, ma'am. My screen is visible, ma'am.
Yes.
Yeah, my
You may
voice is
proceed. Yes, it
my
is
voice
clear.
is audible, ma'am. Yeah.
Yes.
Yeah, Dr. Mageshwari. Yeah, okay.
Yes, ma'am.
Just okay now. Okay.
Yeah.
Now.
Thank you, sir, and thank you, ma'am. Good evening to everyone present here. Myself, Maheshwari, Assistant Professor, Vistas from Chennai. My topic regarding for this presentation is synthesis and characterization of bio-modified titanium dioxide nanoparticles and their biological applications. My outline of my presentation comprises about introduction, synthesis, results, applications, and summary. The need for the day. We all know how you can see the earth is crying because of pollution everywhere. Water pollution, air pollution. Because of this, there are so many several diseases regarding bacterial wise as well as viral wise. Now, could you hear about this pandemic situation, the corona, the COVID? All these things is happening right now. We want to live in such a hospitalized earth, or we want to live in a happy earth atmosphere. We all love to enjoy the happy and peaceful earth. How can we achieve this? It is not an ordinary thing to achieve directly, but step by step we can. do this process. Now, we have taken a very particular based technology, the nanotechnology. It's a field of applied science where the matter is controlled on an atomic and molecular scale. In the synthesis of the technology, we have two different processes. One comes under the bottom-up synthesis and the another one is top-down. We have chosen the bottom-up synthesis where small atoms, they combine together to form clusters and they combine to form together as nanoparticles. Now we have to, under this bottom-up synthesis technology, there are several methods, salt gel applications, spray pyrolysis, so many methods are there. We have chosen hydrothermal technology. It's nothing but a chemical reaction where it is taken above room temperature and also pressure is more than 1 atmospheric pressure. Now, why we need to choose this hydrothermal? The reason is the starting source material is very inexpensive. And also you can control the parameters for taking the size, the shape of that particular particles. That's the reason we have chosen hydrothermal technology. And then the next thing is, okay, we have taken for hydrothermal. Then what material we have to choose? We all know the application which we are going to go for is biological, which means here we are going to study about the antibacterial nature. And titanium dioxide, it is popularly known as a very excellent photocatalytic material. Because of its high surface area, there will be more number of microbes will be coming into contact. Because of the small crystalline size, they will be able to penetrate farly inside to the tissues. Like this, you have the anatase form, the high crystallinity, porous structure, activation of light source. So these are some of the properties why we prefer this titanium dioxide nanoparticle. Now, the synthesis process comes under here, where you can see this, the titanium tetraisopropyl. This is a precursor, starting precursor. This, along with isopropanol and deionized water, it is mixed nearly for about, stirred in the magnetic stirrer for 2 hours, and then it is transferred to an autoclave and maintained at 200 degrees centigrade. Then it is centrifuged and dried in oven, and then annealed around at 350 degrees centigrade, where we obtain titanium dioxide nanoparticles. Now, after obtaining the particles, we have to undergo for characterization. So we have gone for the characterization of XRD. From the XRD analysis, we were able to see it is a highly crystalline in nature, and the anatase phase of JCPDS file number 211272 exactly matches with this. Coming with the FTR analysis, the spectrum with 633 centimeter, it shows a strong stretching vibration of TiO-TI bond. And from the UV analysis, the maximum absorbance has been around 264 nanometer. Now, coming for the next characterization, which is in a biological. What is antibacterial nature? Preventing or destroying the growth of bacteria with the agent. So basically, we should understand what is bacteria. While we talk about, there are two categories, gram-positive and gram-negative. In the case of gram-positive, you can see a brown color layer, which is a thick peptidoglycan layer. Whereas in the case of gram-negative, this peptidoglycan layer is very, very thin. There is a presence of outer membrane, which is comprised of lipopolysaccharide and protein. This is absence in the case of gram-positive, and this forms one of the important mechanisms for the antibacterial activity. Now, we have chosen 5 organisms. Out of that, Escherichia coli, Klebsiella pneumonia, and Pseudomonas falls under gram-negative. Staphylococcus aureus and Streptococcus mutans, they fall under the category of gram-positive. Now, there are several methods available for testing this antimicrobial nature, such as well diffusion, disc diffusion, micro dilution, macro dilution, like that. We have chosen disc diffusion technology. Now, here, the agar plates.
Excuse me, Maheshwari.
Yes,
There's
ma'am.
a reminder for you. 4 minutes has exceeded. Trying to wind up in another 1 minute.
Yes, ma'am. So, which means here the plate is fully inoculated with bacteria, and then it is incubated for nearly about 24 to 48 hours, where you can see the zone of inhibition. Now, based on this result, we can easily see the zone of inhibition is maximum in the gram-positive bacteria. Now, the next process is, why can't we modify it with biological thing? So we have gone for ginger extract, and we modified this with titanium dioxide. So based on that, the XRD pattern analysis and the FTR spectra and the UV analysis, they have shown clearly the maximum absorbance has increased to 320, which clearly the ginger has been modified over the titanium. There is a compound called gingerol, which is C double bond O bond, which is around 1642. You can see a clear change here after modification with the titanium dioxide nanoparticles. Now, based on the antibacterial nature, we have seen the enhancement of antibacterial nature due to the modification of ginger. You can see even the gram negative as well as the gram positive has attained nearly about 16 to 18 millimeter of zone. This clearly understood that we have taken the summary as the pure and the ginger modified has been tremendously synthesized using hydrothermal, and the characterization has been done, which proves that from XR it is highly crystalline. The maximum absorbance has increased in the UV spectra, and on the whole, my conclusion will be the modification of ginger has enhanced the antibacterial nature. These are the references. Thank you. And our paper is published in the Elsevier journals. And also, I give my acknowledgement to Shizuoka University, Japan, for the TEM analysis. And one more thing, since because of the time limit, I'm not able to show the paper fully. So this is what is the paper. It was published. So you can see the anti-cancer application also is available here, where we have undergone the cell viability test. And this is the TEM analysis where we have seen for ginger, turmeric, and garlic. Even IIT Madras, they are undergoing this particular process in turmeric. And this is about the HR-TEM analysis. And regarding the anti-cancer activities, we have seen this is a MTT assay analysis, which clearly enhances even the biomodified titanium dioxide nanoparticles. They have enhanced the anti-cancer applications also. Thank you. Thank you, ma'am, and thank you, sir.
Yes, Maheshwari?
Yes, ma'am.
Thank you for the neat presentation.
Thank you.
And now I have a small doubt. Can you tell me the thermal stability of your material? Because you have annealed it at 300 degrees
No, ma'am.
Celsius.
Actually,
So
what?
I just wanted to know the thermal. Yes, tell me.
Yeah,
Proceed, proceed.
yes. Actually, ma'am, in the case of thermal stability, we have undergone only for TiO2, because while we are annealing the thing, the titanium dioxide nanoparticles we have separately synthesized using hydrothermal technology. And after that, we have taken a sample, that is, for example, 0.2 grams of the powder, and then it is mixed with the ginger extract. Because we know that the ginger, there are so many number of molecules present inside the ginger. So if you go beyond 60 degrees centigrade, we will not be able to have all those molecules, this gingerol, etc. and all. So what we have done is we have not done annealing for the biomodified titanium dioxide nanoparticles.
Okay, fine, good. If any of the participants have any doubts, you can clarify it in the chat session. Now, because of time constraints, we can move on to the next participant, OP number 80. And thank you, Maheshwari, for the neat presentation once again.
Thank you, ma'am. Actually, I have to give my acknowledgement to SRM University, to my guide, Dr. S. Ponusamy sir, the controller and the registrar of SRM University. And also, I have to thank Dr. Hayakawa sir from Shizuoka University, Japan, for giving me all this analysis experimental wise. And I have to thank the PPG College staff members for giving me an opportunity to give an oral presentation here. Thank you, ma'am, and thank you, sir.
Yes, thank you. OP number 80, are you ready?
Ma'am, Pavai ma'am?
Yes. Yes, sir.
I think 80 is not ready. So you call OP
86.
number 90, RJ Vaidya.
Sir, what about OP number 86,
90,
sir?
I think they are not ready.
Okay, sir. Then shall we move on to OP number 90?
I'm 86.
Yes, OP number 90. Is OP 86 ready?
Yes, madam, I am ready.
Yes, ma'am.
Yes, then OP 86 can start with your presentation.
Okay. Just a minute.
OP number 86, can you share your screen?
Yes. His screen is visible, ma'am?
No?
I'm not able to share the screen, ma'am. I'll present later on after this.
Yes, okay, no problem. OP
I call
86
Vaidya.
will be. Yes,
Vaidya.
now OP 90.
Yes, sir. Yes, sir. I'm ready. OP number 90.
Yes. You may start presenting your screen.
Is it my screen is visible, madam? My screen is visible. My screen is visible.
Yes, sir. You can proceed now, sir.
अभी दूसरा कोई
Okay,
प्रेजेंट
okay.
कर रहा है यहाँ पे है स्क्रीन पे लेकिन वो कुछ अलग ही दिखा रहा है
Yes, yes. You may proceed. You have a clear video and the audio.
Okay. Good afternoon, all of you. So today I am going to present my work on thickness-dependent phonon transport in few layer black phosphorus and effect of anisotropy on this phonon transport I am going to discuss today. Myself R.G. Vaidya from Department of Physics, Tumkur University, Tumkur. My presentation consists of introduction, theory part and resultant discussion with the final conclusions. We have done the theoretical work on the phosphorine, that is the exfoliated single layer black phosphorus, which is one of the 2D materials. Phosphorine is observed to exhibit extraordinary properties such as anisotropic structure and anisotropic electrical and thermal properties are also observed in case of black phosphorus. This anisotropy is observed to arise from the anisotropic phonon dispersion, which is going to be observed in the zigzag and armchair direction of the few layer black phosphorus. Experimentally and theoretically, it was reported that the lattice thermal conductivity of black phosphorus is also anisotropic. This anisotropic thermal conductivity of BP, that is black phosphorus, is very advantageous for practical thermoelectric applications. Phosphorine is a good semiconductor material and also exhibit the thermoelectric properties, and because of that, it can be used in optoelectronics and thermoelectrics. In the present work, we have done the theoretical investigation of lattice thermal conductivity employing the Boltzmann transport formalism. We have studied the explicit contributions from dispersive transverse and longitudinal phonons to the lattice thermal conductivity of black phosphorus. And also we have carried out the work on thickness dependent mode wise lattice thermal conductivity of zigzag and armchair black phosphorus and effect of anisotropy also investigated. So phonon are having two modes, the transverse mode and longitudinal modes. The contribution from these two modes to the total lattice thermal conductivity of black phosphorus is rarely reported, and this has motivated us to work on this mode wise contribution on contribution to the lattice thermal conductivity. In theory, we have employed Boltzmann transport formalism in which Holland model has been used. Holland model gives the opportunity to calculate the contribution from low frequency transverse phonons, high frequency transverse phonons, and longitudinal phonon contributions to the total lattice thermal conductivity. We consider the scattering of phonons by boundary, isotopes, impurities, and other phonons via Umclamp and normal processes. These Umclamp and normal processes are three phonon scattering processes in which Umclamp process is non-conservative and normal process is observed to be conservative process, and and they highly influence the phonon transport in case of semiconductors and also in black phosphorus. So here we consider the low frequency transverse phonons are scattered only by normal processes, and Umclam process is observed to begin at the halfway of the Debye frequency, that is half of the Debye frequency, at which the phonon velocity is observed to vary for black phosphorus, and that has been extracted from the phonon dispersion curve done using first principle calculations. These three expressions gives the uh, contribution from low frequency transverse phonon, that is KT1. KT2 represents the high frequency transverse phonon contribution to the lattice thermal conductivity. KL represents the longitudinal phonon contribution to the thermal conductivity. And these are extracted from the Holland model, which is based on Boltzmann transport formalism. Coming to the result and discussion, we have investigated the thermal conductivity of black phosphorus along zigzag and armchair direction. In this figure, red curve indicates low frequency transverse phonon contribution. Green color indicates the high frequency transverse phonon contribution. Blue color curve indicates the longitudinal phonon contribution to the total thermal
Excuse me,
conductivity.
RJ
Black
Vaidya, sorry
curve
for the
indicates the
interruption. You
total
have
thermal
exceeded 4
conductivity.
minutes and you have only 1 minute.
Okay, I will
Try to
complete.
wind up your presentation within a minute.
So it is
Yes,
observed
proceed.
that our calculation indicates that the experimental results are exactly in agreement with our calculations, and it is observed that transverse phonon contribution is observed to be more in case of black phosphorus along zigzag and armchair direction. This figure indicates the nanoscale black phosphorus samples. Here it is clearly observed that longitudinal phonon contribution is very less in armchair direction, whereas in the zigzag direction, both transverse and longitudinal phonons contribute equally. This figure indicates the percentage contribution from high frequency transverse and low frequency transverse phonons, including the longitudinal phonon also. Finally, the conclusion is the transverse phonon play major role in thermal transport both along zigzag and armchair direction. Longitudinal phonon contribution is observed to be less in low thickness black phosphorus sample. It is observed that high thickness black phosphorus sample have both transverse and longitudinal phonon contribution. Our theoretical investigations are in good agreement with the recent experimental data of thermal conductivity that was shown in this figure, where symbols are showing the experimental results. So these are the references, and it is open for the discussion. Thank you.
Yes, thank you, RJ Vaidya. Is there any doubts or clarifications needed from the participant side? If you have any other doubts, you can proceed it in the chat section. Now we may move to the next participant, OP number 115.
Yes, ma'am.
Okay, thank you all of you for giving me opportunity. Thank you one and all.
Yes, thank you, RJ Vaidya, for the nice presentation. OP number 115, you can start sharing your screen.
Thank you.
Okay, ma'am. Just a moment. Hello, ma'am. Are you visible?
Yes, both your audio and video is clear. You can proceed.
Okay, ma'am. Yeah. Good afternoon, everyone. And myself, Shaktivel Kumaravel. I am a research scholar in, and now I am working in National Taipei University of Technology, Taiwan. Today I am going to discuss about thermoregulated synthesis of NIM and layered double hydroxide for real-time determination of hydrogen peroxide in live cells and oxidase activity. This is my outline, introduction, research and discussion, conclusion. First, hydrogen peroxide. Hydrogen peroxide is a rebound reactive oxygen species and byproduct of cellular metabolism, which plays a crucial role in physiological process. It has been extensively used in food, textile, paper, and pharmaceutical industries, etc. For excess production of endogenous formaldehyde leads to the DNA damage and create cancers and Alzheimer's disease, etc. For normal range of peroxide is 1 to 700 nanomolar. And next, uh, uh, transition metal-based layered double hydroxide. In transition metal-based LDH have been extensively developed for the effective electrocatalyst for electrochemical energy conversion and storage techniques due to the ultra high surface area, rich active surface, and they're having the structural morphology, chemical compositions, etc. They having more advantages like low cost and biocompatibility, high mechanical stability, high electron transferability, and high surface area. In electrochemical storage and supercapacitors, they are using a variety of transition metal-based LDHs like FEMN, FeCO, NIMN. Today, we are choosing for further experiment NIMN. Moreover, in recent years, there are numerous amount of analytical platforms developed for the detection of hydrogen peroxides like chemiluminescence, electrophoresis, GCMOS, fluorescence spectrometry, HPLC. These instruments having their some limitations like it needs prolonged assay time, disease pre-sampling, and is not applicable for work with turbid samples. Overcome with the limitations, electrochemical methods having the more advantages like rapid stability and accuracy. It work with turbid samples and colored samples as well as. This is the systematic representation of overall concept like preparation of nanomaterials and after that go for applications. First, for preparation of nanomaterials, manganese nitrate hydrate and nickel nitrate hexahydrate and HMT is a hexamethylene tetraamine. They are mixed and stirred for 15 minutes and go after that hydrothermal for 24 hours for different temperatures like 60 degree, 120 degree and 180 degree and 240 degree Celsius.
Excuse me, Shaktiven Kumaravil. Already
Okay.
you have exceeded 4 minutes. Try to wind up your session in another 1 minute.
Okay, thank you.
Yes, you may proceed.
For this characterization, FEM images for figure C is FE NIMN LDH at 180 degree shows the clear structures as well as the synthesized NIMN was confirmed by the GCPDS 380715. It also for elemental mapping the presence of elements Ni and Mn. For after that prepared nanomaterials go for electrochemical studies for over nanomaterial with peroxide with a different concentration from 1 millimolar to 5 millimolar, it linearly increased. Next, for current time response of nanomaterial modified electrode for over 16 nanomolar to 9.3 millimolar. For after that, we calculated the LOD 2.5 nanomolar and figure C representing the modified electrode with peroxide and over different interference compounds. For over different interference compounds, it does not show any response. It's more selective for only for hydrogen peroxide. And next, reduction of oxidase activity. For oxidase activity, glucose and glucosidase enzyme with water to form peroxide. This reaction will confirmed by the experiment. After that, for catalysis is a scavenger of peroxide. And for real-time analysis, we chosen for two normal cells and one for cancerous cells. For this figure A, B, and C are the IT curves of three different cells with stimulants. For figure B is the first two normal cells producing low amount of peroxide, and over the cancerous cells produce highest amount of hydrogen peroxide. And conclusion, for we successfully synthesized four different types of four different temperatures of nanomaterials, and it has the linear range 6 to 9.3 millimolar, and it shows the lowest reduction and good selectivity as well as stability. Used to modify electrode to quantify endogenous hydrogen peroxide in live cells. And thank you. Finally, I have to thank my advisor, Professor Shen-Tang Huang, and finally, I have to thank PGP College of Arts and Science for giving me this opportunity.
Yes. Thank you, Mr. Shaktivel Kumaravel. Thank you for the neat presentation. If there are any doubts from the participant sides, they can climb it in the chat session. And now we'll move on to the next OP session, OP number 178. OP 178, are you ready? Is OP number 178 ready? I think OP number 178's audio is muted. Can you just unmute your audio and start your presentation? OP 178. Am I audible to the participants?
Madam, am I audible? Yes,
Yes, sir. Thank
okay.
you, sir. I think OP 178 has got some problem and struggles in sharing a screen. So shall we move on to the next participant, OP number 183? Are you ready?
Yeah. Is it visible, madam? 178, madam?
178.
Hello?
Yes, no, sir.
178
Your screen is not
is it
visible.
visible, madam?
No, your video is not clear, sir.
Hello? Okay, ma'am. Okay, I will try afterwards. Okay.
Yes, okay. In that case, we'll move on to the next participant, OP number 183, S. Abhirami. Is the next participant ready with your presentation?
Yeah, I'm ready.
Yes, you may start presenting your. You may start presenting.
Yeah. So I'm audible?
Yes, you're audible and your video is clear.
So my topic is So this is studies on structural, electronic, and magnetic properties of Li3 ion substituted HO2 FeMnO6 double peroxide compounds. So objective of my presentation is introduction, material preparation and characterization, experimental procedure, results and discussion, conclusion and references. So some introduction about ceramics. Ceramics is nothing but a non-metallic inorganic solid. So therefore all inorganic semiconductors are ceramics. So by describing a material, it used to be a ceramic when it is melted at the reverse extreme. If we cool some ceramics sufficiently, they become superconductors. So all the so suppose high temperature superconductors or ceramics. Some applications are they are used in general solar cells in okay. Some introduction about the perovskite compounds. The structure of single perovskite compound is AbO3. Then these compounds can attain electronic structure ranging from insulating to metallic and even half metallic with spin polarized electronic conductivity. So further, the perovskite compounds can illustrate superconductivity, magnetic ordering ranging from the anti-ferromagnetic to ferri and ferromagnetic, but can also demonstrate magnetic frustration with no apparent long-range orders. Some introduction about the double perovskite compounds. AB double prime O 3 is the double perovskite structures have been reported with a broad range of implications such as structural distortions, order disorder phenomena of the B-side cations, electronic band structure and magnetic ordering. It is well known that the compounds with properties such as spin polarized electronic transport, high dielectric constant, low thermal conductivity or multiferricity are the key players for the future technologies. So, however, many of these compounds accounted in the literature have not been thoroughly examined, and it was partially the reason of this work to bring out such cases in order to find novel compounds with useful properties. So, materials preparation and characterizations in this work. So, I'm taking holmium 3 oxide, iron oxide, magnesium oxide, lanthanum oxide. Also, to analyze the various properties of the prepared compounds, I am using X-ray photoelectron spectroscopy, powder X-ray diffraction, scanning electron microscope, and energy dispersive X-ray analysis, DRS, and Raman spectroscopy, vibrating sample magnetometer, and photoluminescence spectroscopy. So, procedure. So, under the controlled condition of temperature and time, the conventional solid-state reaction technique has been employed and synthesis the HO2 FeMnO6 compounds. The high purity powders of the HO2 O3, Fe2O3 and Mn2O3 compounds taken in proper stoichiometric proportions and well ground using the agate mortar and pestle for 1 hour. See, in the air atmosphere, the powder was initially sintered at 1100 degrees Celsius for 12 hours. The samples as well ground again and sintered at 1200 degrees Celsius for 12 hours. To obtain the homogeneous mixture of the compounds, the procedure has been repeated for 2 more times. So, see in the holmium, so I am taking the properties of HO2 MnO3 and HOFeO3 materials are also the important in the discussion of the properties of double perovskite of the newly prepared compound. These are there was no more intense work found in this series of the HO2 FeMnO6 compounds. Hence, for the continual search for the peculiar properties, substitution of the La2O3, A site of the HO2 FeMnO3 compound has been carried out in this present work. So these are my results. So first is photoelectron spectroscopy. So in this, the HO2 FeMnO6 compounds in the 5 different compositions so are characterized to say, okay. So for every sample, the survey spectrum was recorded initially and then The closed window screen of elements of HO, LE, FE, M, and OC was performed. These are all my spectrums of.
Excuse me, Abhirami. Yes, I think you have exceeded 4 minutes, so you have only 1 more minute left.
Okay,
Try to
okay.
wind up
These
your
are all my
presentation
results.
within a minute.
These are all the binding energy values of C1s and OS spectrum of my prepared compounds. So, and the binding energy values of the elements obtained from the XPS spectrums are shown here. My another characterization techniques used are the XRDs. These are all the spectrum of the pure and the LA doped HOT, FE, MnO6 compounds. So, and these are all the obtained Ritwill refinement values is. Then the structural parameters of the pure and LA doped compounds are shown in here. So the prepared compounds or all are in PBNS phase group. These are all my Raman studies, micro Raman studies. So and the fitting curves of the Raman signaling from the HO, the HO to FEM and O6. So and two more combinations are shown in the figure. These are all my assignment Raman modes of the prepared compounds. These are the SEM and the EDAX images of my compounds. This is the magnetization curve obtained in the LA prepared compounds. Conclusions. So the phase stabilization of the double perovskite HOT, FEM and O6 compounds has been carried out. So under the conventional solid state reaction technique, the Ritwill refinement confirmed the double perovskite orthorhombic structure PBNM space group, the pure and the LA substituted compound. The continual variation of the Raman resonance modes of the vibrations implies the improvement of the incorporation of the La3 plus ions into the double perovskite crystal structure of the parent compounds, and the SEM images reveal the substitution of La3 plus ion does not change any on the morphological structure of the prepared compounds, and the effective variation in the intensity of the photoluminescence may be due to the fact that the presence of the structural distortion enhances the change in separation of the leads to the drop of carriage mobility. Then directs the reduction of the electron hole recombinations rate. Then the linear variation in the magnetization studies reveal the anti-ferromagnetic property of the pure and La substituted compounds. Further, the slight decrease in magnetization with respect to the increase in concentration of La3 plus ion. Then, hence, the magnetic interaction in the magnetic chain decreases on the basis of the results obtained from the various characterizations. If is to be noted that the HOT, FEM and O6 compounds may prove to be promising candidate for various applications in the field of higher density information recording media, spintronics, magnetic field sensors, and infrared detectors, among the many of other applications. So thank you. Thank you so much. Thank you for the opportunity.
Thank you, Abhirami. Yes, it was a nice presentation and you have given more information. But one suggestion from our side is that you have given more points to the introduction, but you have not focused on the results and discussion in detailed manner. So from the next presentation, we expect you to give the clear and detailed expressions for your results and discussion.
So for 5 minutes, I am just like I short my results and discussion.
Yes, while cut shorting your presentation, just cut short your introduction part and give more details to the results and discussion part.
Okay, sure. Thank you so much.
Yes, thank you. Thank you for the nice presentation. And if there are any doubts or the clarifications from audience side, you can post it in the chat session. So now we'll move on to the next presentation, OP number 195. Is OP 195 ready? Yes, if yes, you can proceed with your presentation OP 195. Mr. JC Mahatu, I think your audio is off. Kindly unmute your audio and start your presentation. Be quick. I think there is a problem with OP 195 in sharing the screen. So if OP 80 is ready, we can move on to OP 80. Or OP 86. There's a call for OP 86.
Yes, ma'am.
OP 86 can proceed to start.
Ma'am, JP Mathur is already presenting. Mr. Mathur, you're not
OP
audible.
195, video is clear. Just try to unmute your audio and start your presentation OP 195.
Okay. Okay, ma'am. Thank you. So today I shall talk on growth of self-organized nanostructures, epiaxial iron disilicide and cobalt disilicide nanostructure on medicinal silicon 1117 by 7 surface. I have chosen cobalt disilicide and iron disilicide nanostructure growth because it is one of the important material used in semiconductor industry for interconnector, and also the low dimensional structure manifests some of the phases of iron disilicide semiconducting, and also magnetic properties. So that's why I have chosen to investigate the growth of iron disilicide and cobalt disilicide. So we have investigated this at Icecs Kolkata in this MBA STEM system. So for the growth, we have chosen silicon wafer. So silicon wafer, as you know, possesses oxide layer. So first we remove the oxide layer by standard thermal cleaning procedure. For that we heat the silicon substrate by resistive heating at 500 degrees Celsius for 2 hours. Then pass direct current through it and heat it for at 700 degrees Celsius for 14 to 16 hours. And then for 1 minute we flash it at 1250 degrees Celsius. When we rise the temperature of the silicon wafer to 1250 degrees, the oxide layer gets removed. And then we bring down the temperature at 870 degrees Celsius, where the top layer atoms rearranges themselves to get minimum energy configuration, or this new rearrangement is called this phenomenon is called surface reconstruction. So we found that in silicon 111, 7 by 7 unit cell is the or reconstruction is the lowest energy reconstruction of in 111 surface. So that means the unit cell surface unit cell is 7 times higher than the bulk ideal 1 by 1 unit cell of silicon. So on this is the so we have taken a vicinal surface. So vicinal surface means that the offcut angle is higher. So here we chosen 3 plus minus 0.1 degree offcut angle. So this is a large area STM image of the clean atomically clean silicon surface, and this is a closed view. And here we can see the atomically clean flat top surface where the atoms are arranged regularly. This is one 7 by 7 surface unit cell. We have taken a line profile. From that we can found that really the surface offcut is nearly 2.9, that is 3 or 2.9 degree. So on top of it, we have deposited iron at elevated temperature, substrate temperature, that is 600 degrees Celsius. So when we deposit iron on this clean atomically clean silicon surface, the iron reacts with the silicon substrate silicon, and it forms iron silicide. So this is the STM image of the iron silicide grown nanostructure on the silicon 111 vicinal surface. So we found that the iron silicide grows as a nanodot or as a nanorod or nanoware, and we could see that the top surface is a new reconstruction, and the primitive initial of this is root 7 and by root 6. So our idea was to, and this is another image of the iron silicide grown nanostructure, and here we clearly see that the iron disilicide nanowares actually has distinct facets, 4 distinct sidewall facets, and a top flat top surface of 4 to 5 atomic separation wide. And the silicon surface, we can see from this STM image close view that it contains the 7 by 7. The 7 by 7 reconstruction is intact. That means that the iron disilicide grows as a island growth or Hallmark-Weber growth, Hallmark-Weber growth. So our idea was to grow another kind of silicide on this on top of this iron silicide decorated surface. So for that we bring back this iron silicide template surface to the growth chamber and deposited cobalt at 600 degrees Celsius. And cobalt also reacts with the silicon surface. The metal silicide actually very reactive with the silicon, and it forms a silicide. So we can see new triangular type of triangular and few trapezoidal type of nanostructure has been grown from the STM investigation. So these are the newly grown cobalt disilicide nanostructure which was absent. So also from the AC.
I think we have exceeded 4 minutes, so try to wind up your presentation in another 1 minute.
Okay. So for the compositional confirmation, we did XPS measurement, and this is the cobalt 2p, cobalt iron 2p, and silicon 2p, and oxygen 1s XPS data. That the open circles are the data, and we have heated it, and from this we can confirm that the cobalt disilicide, iron disilicide has been grown on the silicon 111 surface. So in conclusion, I would say that we have investigated the growth of OS self-organized epithelial iron disilicide and cobalt disilicide nanostructure on a same surface, that is vicinal 1117 by 7 surface. So iron disilicide preferably we see that grow as nanowire on the vicinal surface, and while the cobalt disilicide grows as a nano island on the vicinal surface. And here we use the fact that the iron disilicide is thermally stable at the growth temperature of cobalt disilicide. And I would like to acknowledge my collaborator and seniors, and thank you for your kind attention.
Thank you, Mr. JC Mahato. I think you have a question in the chat session. If possible, you try to answer that. Okay. Answer the question in the chat session itself. Okay. And thank you for the neat presentation. Now shall we call upon OP number 86 for the next presentation?
Yes. Is this screen is visible, ma'am?
Yes, screen is visible and your audio is also clear. You may proceed.
Okay. Good evening to all. Myself, Dr. Jyotsna Pandey, Assistant Professor, Department of Physics, KC College, Mumbai. My topic of presentation is growth, micro-hardness and NMR studies of an oxalic acid drop, organic NLO crystal.
Excuse me, Joseph.
Here, let me introduce the topic.
It's not clear, only your screen is visible. We couldn't see your presentation.
Yes, ma'am. Hello.
Yes, Josna. Your screen is visible, but
am I audible?
You're audible, but your presentation is not clear. Your screen is visible, but your presentation is not visible. You have shared some other tab.
Okay, ma'am.
Try to share your PPT.
Now it is visible, ma'am?
No.
Please excuse me, ma'am.
Hello, excuse me, madam.
JC
178 is ready.
Yes, sir.
178 ready, madam.
Already OP86 is presenting, so you may wait and you may start your presentation after OP86 completes your presentation.
Okay, ma'am. Okay, ma'am.
Yes, sir.
JC Makato, I think you have question from Dr. GK in comment section.
JC Mohato, try to give answers for all the questions raised in the chat session.
Ma'am, my screen is visible now?
Yes, but we couldn't see anything. It is clear. A plain blank PPT.
Blank? Now, ma'am?
No, Josna. We could see only the blank presentation.
Yes, ma'am. Ma'am, you can give chance to other personnel.
Yeah, Pavai,
Sure. Yes,
yeah,
sir.
please call other person. Call other person, please.
Now OP 178 can present your order.
Okay, madam. Okay.
Yes, if you are ready, OP 178 can start your presentation.
I am ready, madam. I'm ready.
Yes, proceed, sir.
Madam, am I audible and visible?
Yes, sir. Yes, sir.
Hello?
Yes, you're audible.
Is it
You
visible?
are audible, not visible, sir.
Okay, madam. Sir?
Your video is not visible, sir, but your
Is
audio
it
is
visible?
clear. Try to share your video. OP 178, try to stop your video and share your screen.
Participants,
Madam, is it visible, madam?
No,
Hello?
sir.
Krishna Pandit, just wait.
Yes, sir. I'm not able to.
Venkateswarappa, sir. Dr. Venkateswarappa. Venkatavaranappa.
Sir, is it audible?
Sir, you are
Am I
audible,
audible,
sir.
sir?
Yes, sir, but your video is not visible, sir. Now, Josna is presenting, sir. Josna, please share your
Okay,
screen.
sir. Okay, sir.
Sir, I'm trying, but as you're saying, it's blank. So I can see my presentation on my screen.
Okay, just a minute. Thank you for active participants. So, small announcement. The posters received from that participants are presented in websites. Those posters are not available in website page. Please mention your poster number, EP and something number, EP 269 or 261 number. Please message me. Today night we will update. So for participants, please visit the website page and the e-poster section. So e-poster section, you comment any poster. If you want any suggestion or clarifications, you post the comment, your name and mail, your comment. First time we will approve your mail ID. From second onwards, you just comment the mail ID and your questions. So second time you don't need the approval. So please, any posters you will first time you will I will give the approval for your mail ID. So please comment any posters. Thank you. Jyoshna Pandey.
Sir, I'm not able to present now. Sir, there is a present now. I'm clicking on that. So I can see your entire screen of window. Just please guide me, sir, what to do.
Please send your presentation to our PPCAS mail ID, ppg physicsas@gmail.com mail ID. So we will share from here. Dr. Venkataranappa, you can proceed. Is this possible now for you?
Sir, that email ID, no, Mohan Kumar, sir.
No, no. ppgphysicscas@gmail.com.
Okay, sir.
How are you call other
Mohan Kumar,
presenter?
yes, shall we invite OP 178 to join? OP 178.
Sir, please tell me email ID, sir, please. Hello, sir.
Yes, proceed.
Sir, please give me your email ID, sir, so I can send my presentation.
Chat box I will already posted, ma'am. ppgphysicscas@gmail.com.
Okay, sir.
Yeah, we have received 8 comments from the posters. So we all approve that all the comments so that participants can post comments in any posters. The same way, I request all the participants to comment any poster section. Pavai,
Yes, sir.
shall we proceed or wind up the session? Tomorrow we will continue.
Yes, sir, no problem, sir. We have 2 more participants from
Sir,
today's session, sir.
Just a
Sir, I
minute,
have
just a minute.
sent my email, sir.
Okay.
Sir, I have sent my presentation.
Do you want me to wait for Jyotsna to present, sir?
Just a minute, I will receive the.
Okay, sir.
Yes, no?
Yes, sir.
Now I share your PPT, you continue. When you say next, I will move on next slide.
Sir, I think OP number 178 is sharing its screen. Yes. Now the presentation of Jyotsna
Just a minute,
is ready. I think OP 86 is ready to present.
So I can start?
Yes, Jyotsna, you may start.
Good evening to all. Myself, Dr. Jyotsna Pandey, Assistant Professor, Department of Physics, KC College, Mumbai. The topic of presentation is growth, microhardness, and NMR studies of an oxalic acid drop organic annular crystal. Next. Sir, next. Let me introduce the topic. The growth of crystal and the theory of crystal growth continues to be an area of central importance and increasing activity in material science. In search of new electronic material, crystal growth plays an important role. Take, sir. The basics of crystal growth. The growth of crystal can be considered to compress the following steps like achievement of supersaturation and supercooling, formation of crystal nucleus of microscopic size, and successive growth of crystal. Next. Why I have selected amino acid? Because amino acids are very interesting organic material for NLO devices as they contain donor carboxylic COH group and proton acceptor NH2 group known as deuterium, which creates hydrogen bonds. The NLO material are backbone of various industries such as photonic, optical and electro-optical switching, medical AI due to wide range of potential and technological application. Next. The importance of NLO crystal is the growth of highly efficient NLO crystals for visible and ultraviolet vision is important for both laser spectroscopy and laser processing. They have wide application in the field of telecommunication and optical information storage devices. Next. Importance of organic crystal. So I'll explain the importance of organic material. As you can see, the organic material shows superior NLO property due to their pi conjugate. Click. So next, electronic system and donor and acceptor. Organic material shows fast and large nonlinear response over a broad frequency range and high optical damage threshold. And the organic material which I have selected is oxalic acid, COOH twice. Next. The growth of crystal, the basic growing methods are growth from melt, growth from solution, and growth from vapor. So I have selected low temperature solution growth. Next. Slow evaporation technique. This is the most successful method for crystal growth. In this method, the component can be dissolved in a solvent and left for slow evaporation. And slow evaporation can be done under atmospheric condition. Here we can see glycine is one of the component and oxalic acid. They are mixed in 3 different ratio, 3:1, 2:1 and 1:1. Next. And these are the grown crystal for the 3 different series, 3:1, 2:1 and 1:1, where 3 is the ratio of glycine and 1 is the ratio of oxalic acid. So in every combination, 3:1, 2:1, 1:1, oxalic acid component is same and glycine component is changing. Next. This is the biggest crystal growth in my department laboratory, that is 4 centimeter in length. Next. Result and discussion. So let me discuss the micro hardness study. The grown oxalic acid crystal was polished on the most flat surface and are used for micro hardness studies. The diamond indenter was used for indentation purpose at various load, and the diagonals D1 and D2 can be measured directly on the digital display using the average values of measured diagonals and load applied. An important use of micro hardness studies is to find the indirect estimate of the other mechanical characteristics of material having a specific correlation with the hardness. Next. We can see the formula used for calculation, that is Vickers hardness number, VHN, HV is 1.85, pressure divided by D square, that is kg per mm. Here P is the load. Next. Kick proposed an analysis of result on hardness, and according to him, the relation between applied load, that is...
try to wind up soon. We have exceeded 4 minutes.
Yeah, an indentation length D is given by the formula. Click, sir. Next. The formula is P is equal to K D raised to N, and from the calculation it is confirmed that the grown crystal GOA1 is soft crystal. Next. This is the observation table. For different load 10 gram, 25 gram, 50 gram and 100 gram, the GOA1 diagonal size is increasing. Next. This is a table for load and my grown series GOA1 and the name of sample. So according to this observation table and this result, we can prove that. So next. The Mayer's index N values for all GOA1 is calculated as 3.90. And as you can see in this graph, HV versus P is a straight line graph. So it is very clear that as the load is increasing, the hardness value is also increasing. And when the N value lies between 1 to 1.6, they considered as hard. And in my case, it was 3.9. So it is a soft crystal. Next. In case of GOA crystal, it is observed that the plot of log P against log D gives a straight line graph. So the crystal belongs to soft category as Mayer's index is greater than 1.6, and PSR model can be applied to GO1 family of crystals. Next. In NMR study, we can see the NMR study is to confirm the presence of NH2 and CH2 group. Next. So it is very clear in the next slide that I got, so next. Two peaks, one NH2 peak is 3.421 and CH2 peak is 4.683. Next. Conclusion, so new organic GOA crystals of appreciable size were grown from solution method in 2 to 3 week time. The presence of two hydrogen atoms belonging to NH2 and CH2 group have been identified. In HNMR spectra, the crystal belongs to soft category as Mayer index N is greater than 1.6 and PSR model can be applied to GOA crystal. Next. These are the references. Thank you, ma'am, for your cooperation.
Yeah, Pava, any questions?
Yes, sir. Sorry, sir, my audio was off, but I was raising the question. Yes, Jyotsna, thank you for the nice presentation. I have some doubts to be clarified. You have claimed your material to be a NLO material, but you haven't provided any results based on the NLO process. Because if you are promoting your material to be NLO, then you have to give some supporting points for NLO materials, but you have not given any results on NLO materials. That is my doubt.
That studies already have completed NLO study, that is second harmonic generation, but in this presentation I have not included that point. So it is already, I have published one paper on GOA crystal. So it is NLO material, but for this presentation I was concentrating only on micro hardness and NMR studies.
Yes, that's good, but in that case you have to provide your title such that you tell only the hardness studies alone. Okay, don't mention anything about NLO studies or don't give any information on the NLO basis.
Thank you, ma'am.
One more thing.
Yeah, just
yes, and one more question.
Yes.
Yes.
Question by.
Can I proceed with my question?
Yes, no, ma'am. The question by Karthikeyan, Dr. JK. So, any disadvantages? Venkatavarnappa, please mute your mic.
Okay, madam. Okay, sir. Please.
Just a minute, sir.
Am I audible, sir?
Just mute, sir. Mute, please. Just a minute. Okay, sir. Yeah, Jyotsna Pandey.
Yes, sir.
Yeah, question from Dr. JK.
Yes.
Disadvantages of organic NLO materials, and how does the ratio of glycine and oxalic acid affect the crystal structure? Do they form similar crystal structure?
Sir, actually the XRD studies I have completed, but I have not presented in this presentation. So as the concentration of oxalic acid is changing, even in the SHG study, that is efficiency conversion, the efficiency goes on reducing. So that means when the oxalic acid concentration is increases, is affecting my crystal on the bad side. Even in size, even in the case of size of the crystal and the SHG efficiency also. So I find due to large concentration of oxalic acid, the efficiency is reducing. So I suggest the concentration of oxalic acid should be less with glycine. Hello.
Yes, Jyotsna. Is there any doubts from the other participants?
I think no comments. So just we move on the next presentation. I think the last presentation for this session.
Thank you, sir.
Yes, Pavai. Thank you,
Yes.
Josna. Pavai
Yes.
is
Now
listening.
shall we move on to OP 178, sir?
Yes. Yeah. Okay.
OP 178 can start presenting.
Please, sir. Am I audible?
Yes, sir, you're audible.
Please share. Sir, are you sharing my PPT?
Just a minute, sir. Just a minute. I'm doing.
What? Okay. Sir. Yes, sir. It is visible, sir. Sir, myself, Dr. M. Venkataramanappa, Assistant Professor, Government First Year College of Arts, Science and Commerce, Sira of Karnataka. My today's topic is Europium doped magnesium silicate nanophosphor for white LED and latent finger detection applications. Sir. Sir, please. Am I audible, sir?
Yes, sir, you're audible. You may proceed.
Okay. So phosphors means phosphors are the luminous materials which emits light in visible region by absorbing light in UV region. So here we have a host material as well as activator. Activator is a dopant, sir. Luminescent properties are highly depends on size, shape, morphology, composition, and crystallinity. Currently, the research on efficient and low-cost nanophosphors was challenging problem for new luminescent materials. Use of these phosphor material in light-emitting diodes was major step in solid-state lighting technology. The idea, the idea, the ideal morphology of luminescent particle should include a perfect spherical shape and a narrow size distribution and non-agglomeration, which depends on synthesis techniques. Among various silicate families, ferrites host exhibits exceptional properties, low thermal expansion, a stable crystal structure, excellent long-term stability, good solubility, and environmental friendly. Recently, rare earth joined doped luminescent nanomaterials have received an extensive attention due to their technique, properties, and can be used in potential applications in the fields of luminescence devices, optical transmission, bioprobes, medical diagnostics, etc. Sir, please. So the synthesis techniques have been broadly classified into two groups. That is a chemical route. Another one is physical route. So, and a chemical route is also called as a bottom-up route. Physical route is also called as a top-down route. So, under chemical technique, we come across this is the sonochemical synthesis we have adopted. Why we have chosen this? Because it is simple, it is a fast, low temperature required, so convenient for preparation, time saving, economical and environmental friendly, eco-friendly, etc. So thank you, sir. So this is the schematic diagram which is used for the extraction of aloe vera gel, which is used as a surfactant in our synthesis technique. Sir, next. So preparation of Mg2SiO4 nanophosphorus. So stoichiometric amount, we have calculated the known value of given compound, that is called as the stoichiometric amount of magnesium nitrate and tetraethyl orthosilicate were dissolved in 100 ml of distilled water and thoroughly mixed in magnetic stirrer to get uniform solution. The stoichiometric amount of europium nitrate from 1 to 9 mole and different concentrations of aloe vera gel was added to the above results solution slowly. This solution was then introduced to the rare earth sonicator, that is a bath sonicator. Then the different reactions conditions were applied, such as sonication time, varied sonication time, irradiation time. Different concentrations we have used. The solutions was kept undisturbed until white precipitation was formed. Then it was filtered and was washed several times by using distilled water and ethanol to remove the unreacted material. So the product was dried at 60 degrees centigrade for 3 hours in a vacuum oven. So finally, the dried materials is used for the calcination. So these are the two XRD diagrams for our sample. From this XRD diagram, we can say that our sample is crystalline and it is in orthorhombic phase. It is matching with JCPDS number 781371. So the formula which is used for the calculation of crystallite size is D is equal to, that is the K lambda divided by beta into cos theta. This is called as a Serres equation. And also at the right side, that is a B, is the day by
Excuse me,
Serres.
sir. You have exceeded 4 minutes. Try to wind up your presentation in
Next,
another
madam.
1 minute.
Please, next slide.
Yes.
So these are the same images we have got. So this is the for a variation of the sonication time from 1 to 6 hours. So these are the same images. Please, madam. Next. So this is our excitation spectra and emission spectra for our sample. So next. So this is the CCT and CIE diagrams of our sample. So here CIE coordinates from CCT coordinates, the temperature of our sample is around 1992 degree Kelvin. CCT value is around 5000 degree Kelvin are cool colors. So are lower are warm colors. Next. So these are the fingerprints we determined by using a latent fingerprint technique. So next. So these are the different. So conclusions are Mg2SiO4 europium nanophosphorus prepared using aloe vera gel surfactant using sonication technique. So the surfactant, the surface structure of a sample has a different morphology for various surfactant concentration and sonication time. The PL spectra display extraordinarily peaks at 590 nanometer, 612 nanometer, 652 nanometer, and 702 nanometer. The obtained outcomes specify the powder can be efficiently used in detecting the latent fingerprints with all the three ridge features. The prepared nanoparticles can be efficiently utilized in the fields of display devices and advanced forensic applications, sir. So thank you, sir. So this is about my talk, please.
Yes, sir. Thank you for your presentation, sir. It is a nice and a very useful presentation. Thanks for this. And I think you have some more questions in the chat box and try to complete or answer all the questions in the chat box.
Okay, madam. Thank you, madam. Thank you.
Yes, sir.
Yeah, just a minute, Pavai.
Yes, sir.
You have questions from Dr. JK.
Sir, please.
Where does europium 3+ is doped in Mg2SiO4?
Yes, sir.
This is question from JK. Where does europium 3 plus is doping in Mg2SiO4 lattice? Dr. Venkataramba?
Yes, sir. Come on, tell me, sir, please.
Are you understood the question?
I could not follow it, sir.
Yeah, you follow the comment section, chat box. So,
Okay, sir.
what
Okay, sir.
Dr. JK asked is, where
Okay,
does
sir.
your dopant is doped in Mg2SiO4 lattice? Any suggestion or any comments to Dr. JK?
Okay, sir. Okay.
Then another question is this red emitting phosphorus, how can we get white light out of it?
Depends on its temperature, sir. CCT.
Yeah, again, sir asking the two questions. Is it doped in silicon site?
Yes, silicon side, sir. You have to.
Okay. Dr. JK?
Yes, Morgan Kumar, yes.
Yeah, I think you have more questions. I will send the email ID of Dr. Venkatramanappa. You may
Yeah,
discuss.
sure. Yeah, sure.
Thank you. Yeah, Pavai?
Yes, sir.
Yeah, I think all the oral is complete for today's session.
Yes, sir.
Okay, thank you, sir.
Thank you,
I
Dr.
think OP80 is pending, sir.
OP8 is available now, presenting your presentation. I think no more.
Yes, sir. If there are no more presentations, shall we wind up the session, sir?
Yeah, sure, Pavai. Thank you, Pavai, for session there, chair.
Yes, sir. Thank you so much, sir, for providing me this opportunity in the very great international virtual conference.
Thank you. Yeah, thank you all
Thank
for
you,
your
sir.
active participation. We are expecting your valued presence for tomorrow's session, morning session. So,
okay.
Yes, Venkatramanappa, please. Yeah, participants, once again, I request you to post comments in the post session web page. Please go to the web page and discuss with the poster. Thank you all. We will meet tomorrow morning.
Thank you, sir.